this APS Plenary Session. So my name is Mingda, and I represent the APS User Executive Committee. So at the first of this session, so we are going to announce this year's Gopal, Shenoy Excellence in Beamline Science Award. So a little bit of history for this award. It has been used to call this APS User Executive Committee Award a few years ago. And annually, it is awarded to one APS full-time Beamline scientist, regardless of rank. And the key ingredient is for the dedicated and long-term scientific contribution in both research and instrumental advancement, and also definitely support the broader user committee. So for this year, we have about 13 to 14 members in our executive committee. So we took a vote, and I'm really happy to announce this year's awardee, Dr. Zhongho Cai, so a physicist from this X-ray Science Division, and been awarded for this Beamline Science Award. So which we could be there in person to congratulate him, but even if you are there virtually, so let's join first to congratulate for Dr. Cai for this remarkable achievement. So the Dr. Cai, as you can see here, has been working at APS for 30 years, published over 250 papers, and made a few seminal contributions related to micro and nano diffraction and fluorescence, and also imaging and optics. And to be specific, he has been leading this Beamline in Beamline 2 IDD on micro diffraction, and the past few years has been switched the track on this nanoscale, this fluorescence imaging. Beyond that, Dr. Cai has also been designing the various types of these phenol dome plates. So that's from, I took from this Ceramics Society, that's a bulletin, and highlighting this his instrumental advancement. On the right side for this slide, we also have some testimony from the users, and mention that they really have been thanking Dr. Cai for his dedicated support, not only to them, but they passed along this contribution also to their own students and researchers in a very, very long time scale. And I think with that, I hope that Dr. Cai is here and to share this joy for this Beamline award. And beside this award ceremony, and in a few more minutes, we are also going to have a very exciting this afternoon session. The first thing, we'll have this Dr. Jim Kerby to update about the ongoing this APS Plus U status. And then we'll have another Young Investigator Award, Marm Dixit, and to introduce his research on using Synchrotrons to study batteries. In addition to that, we'll also have more the plenary sections to, in different perspective, how to use synchrotron to study like an in-situ characterization, or this functional, this nanomaterials, or there's other parts related to different types of the complementary spectroscopy, or even one session related to machine learning. I think with that, I will stop here. And thank you, Dr. Cai, for all the contribution. And Dr. Kerby, if you are there, I will hand over to you to introduce all the APS Plus U and updates. Thank you, everyone.
So thank you very much, Mingda, for the introduction, and congratulations to Dr. Cai and to all the winners of the awards in the past, in this session and in the past as well. Let me get this teed up for you here. And I think we should be okay there, right? Okay, so I'll talk about the next 30 years, or setting up for the next 30 years, and really look forward to the year ahead. We realize it's not going to be so great from a user perspective, but we think what comes out the other side will be well worth your interest. Obviously a bit anticlimactic at this point, but user operations ended at 8:30 this morning, or slightly thereafter. I'll talk a little bit about the schedule coming up, but after a week of accelerator testing, we're going to turn off the storage ring a week from today, and we will then begin a 1-year shutdown to really remove the majority of the work you see is removal of the storage ring and reconfiguration of things in the storage ring enclosure, the mezzanine, and also experimental floor, and then bringing things back online. And the PSC organization as a whole is working in this. So it's been a great facility. We look forward to making it and as a fantastic user facility in the future as well. So the project scope, has been going on for a total of 13 years now, but it basically is a replacement or renewal of the facility as a whole. You're probably familiar with the long Beamline building. That's basically the only change in the concrete and the civil infrastructure of the building, of the facility, but much of the technical equipment gets removed and replaced, or certainly realigned at a bare minimum. It includes the new storage ring, which is the centerpiece, but new insertion devices for all of the ID beam lines. And this results in brightness increases of up to 100. And there's a specific experimental system scope just in the upgrade, but there's also work going on outside the upgrade. And that's one of the coordination aspects that we really have to take care of. The shutdown hasn't, it started today. We've been working extremely hard to hold that date over the past couple of years. It's been a challenging couple of years, and I've talked about that in the past, and we've succeeded in doing that. And we're ready. Now, one of the reasons you might say, how we're ready, these are just some of the components that we have on site now ready to go. There are 2,245 power supplies on site at Argonne, ready to be installed in the new in the mezzanine area. The numbers across the top just give you an idea of things between costing, which means something's actually here and has been accepted. And obligated means we have a contract in place, although we're still waiting for some things to show up. But fundamentally, the time is now, because there's no more to obligate beyond labor. We've ordered basically everything we can order. It's here. And the time is now to really start installing all this and turning things around. So it's been a long time in the coming. It's been almost a decade since we really got going on this form of the upgrade, and have been working it through the system, and in the past couple of years working with our vendors incredibly closely. There's hundreds of them, particularly in North America and Europe. And we're really doing extremely well in being ready for this. And there's a few pictures to show this. The most critical thing is the modules that we put in the storage ring from our perspective. Without that, of course, it's hard to store electrons. We need 200 of those modules that go into the 40 sectors of the electron storage ring. There's 5 per sector. As of this morning, there are 91 of those completed in every manner. We have about 197 of them that are partially completed, and we're basically been waiting for the vacuum components to show up to complete the installations. So these 97 are done. In red, 1 month in advance of when we actually need them, or when we need them. And you can see we're at least a couple of months ahead of where we need things for the installation. It's been going incredibly well, and the team has been learning as we go. And although not obvious from the monthly data put in here, the slope of this line has been increasing over the past couple of months as we learn, as we modify our procedures slightly, and how we learn how to do things better, which is something we'll continue to do in the future months. Other things you see up in the upper left is motion of one of the insertion devices. This actually is an older photo of the IEX undulator coming in, but we get to do this in reverse with all the undulators. As we harvest things starting today with some components, we will rework some things and then reinstall them for after the upgrade. Front ends, again, we're at the point, this is out in building 981, which is our offsite facility, where at this point, we've done everything we can before actually harvesting the last equipments from the existing machine and reusing them. And to the right is the large power supply for one of the dipoles in the ring. There's 2 of these, one for the M1s and one for the M2s. These are the largest dipoles in the new storage ring. And this has arrived and on site, has been acceptance tested at the vendor, and we acceptance test it again here to make sure that nothing's happened in shipping. So this is the last power supply to be delivered to the APS. The rest of them are here. They've already been through all testing, and the power supply group is ready to go. The schedule that starts with the vertical line on the left here is today, the blue line there, injection extraction timing system, IETS. So for the next week, there will be a change in the frequency of the storage ring relative to the booster, actually the booster relative to the storage ring. And we're testing that change with Beam in the upcoming week to make sure that it works exactly as we expect it to. We've done bench tests of the systems. They've worked fine, but this is the last opportunity since we're turning off the machine to do it for the next 9 months. So it's a way of mitigating the technical risk by running all tests now. If there is something, we can address it over the course of the next 9 months and be ready to start up as efficiently and effectively as possible in the new year. Next week will largely be hazardous energy control. This is locking and tagging out everything in the facility largely, such that we know that everybody working on it, and it won't just be Photon Sciences directorate staff. There's a good number of contractors that'll be working here as well, but we need to make sure every single person is safe. And so next week will largely be focused on hazardous energy control. Beyond that, we'll get into harvesting in detail. There's removal activities going on, tunnel preparation, and installation actually starts effectively the first week of June. There are 40 sectors. They don't all happen at once. And so we go in a sequence. We'll use all 5 super doors. The infield will be extremely busy place. It'll be authorized traffic only. And we will have construction areas identified, including the mezzanine, the storage ring enclosure, and portions of the experimental floor, depending on what's going on in the area. The mezzanine and the storage ring enclosure, starting April 24th, however, will be construction areas. And please, if you're on site, pay attention to all signage, okay, and it's a requirement. You can see other things going in here. We have an integrated plan for all the work going on, not just the upgrade. It's bigger than the upgrade. There's operations work going on in the injector system on the accelerator side, and there's many beamlines that are beyond the upgrade, all the CATs and so forth. All of this must be coordinated in a sensible way. And so we've identified contacts for that work, and we please ask everybody who is involved directly with that to be in touch with those contacts. The feature beamlines are the 9 beamlines specific to the upgrade. You can see the current schedule there. This is driven largely by deliveries from vendors. You've seen at 9ID and 8ID, the new enclosures that are going up. Of course, Hexam and 20ID is already done, the new enclosure out there. And as we go through the rest of these, as the equipment comes in, we use the next year to do the installation and the technical checkout leading to operations commissioning, technical commissioning, and then scientific commissioning in 2024. It's not just about the feature beamlines, however. In fact, there are many beamlines, of course, that aren't feature beamlines that still do fantastic science. And so the beamline restart projection is shown here. This is for all of the beamlines, okay? And we've asked people to work through Robert Winarski largely to let him know of the plans such that this can be scheduled. We want to bring the facility back online in the most effective way. And there's a good number of our users, of you, who don't currently use feature beamlines and are using in the future other beamlines. We want all the users to come back on and be effective users as quickly as possible. So please keep in touch with your Beamline contacts, your Beamline scientists as the schedule. We are going to keep these regularly posted and can be found, and we'll keep you posted on how we're doing as well. So we look forward to the next year. It's a challenge that everybody on the project and Photon Sciences has been working towards for a decade. It's time to make the change in our plans starting now. But we understand absolutely that this is, of course, a fantastic user facility and has been for almost 3 decades. The next year will bring a great deal of changes, and we're looking forward to setting it up as a fantastic user facility for decades to come. So a last note on safety. For those of you who will not be on site, this is a bit off topic maybe, but it's always important that safety is up to all of us. This is a downtime unlike any other. This is, certainly not a 1-month downtime in the past 25 years. And the safety of all personnel is our highest priority. If you happen to be on site, large portions of the experiment hall will be construction areas, and locations and markings will change depending on where we're doing work. We ask you to be alert to respect all signage okay? And assure, do not assume, okay? Don't cross any lines. And if you're unsure, go find a floor coordinator and ask, okay? If you're working on the experiment floor, you need to connect with the floor coordinators as soon as possible to schedule that work. And we'll make sure it gets scheduled safely. There will be something posted on the upgrade and APS pages called the Guide to the APS Shutdown. I'm not going to go through it here, but it's a long thing about safety. We will keep it updated with our schedule and our work plans for each week, and it'll be posted on a weekly basis. And so this information will be available, and we'll keep everybody informed on how it's going. And we look forward to obviously getting to the end successfully. It's really a very quick overview of where we are. We're excited to get on with it. We've done a lot of prep work, and we're really looking forward to setting up the APS for the future. So thank you very much. And if there are any questions, I can answer them briefly here or put them in the Q&A and we can answer them offline. Mingda?
Thank you. Thank you very much. So not questions for now, but I will be the host. So I'll just will be asking if any audience will have any questions about the upgrade status and everything. So you can either type from the Q&A session or just unmute yourself and ask directly.
The attendees can't unmute, so they'll need to put all their questions in the Q&A.
Oh, thank you, Lian. It's good to know. So I guess let's see whether we have any questions from the Q&A. Still have a few more minutes and before the next session.
And if not, I'll say that there is a comms email on the APS upgrade and the APS web pages, and any questions can be submitted there, and we'll post them. Okay.
Thank you, Jim. Maybe I can ask one question. So what we were heard is that it's so for the manpower, they are not working only at one shift, but 3 shifts every day. So that means that 24 hours a day. So is that still the case? How is that?
If I understood the question, it was about the work shifts during the shutdown.
Mm-hmm.
So for the construction, removal, installation crew, and so forth, we're going to work 1 10-hour shift 5 days a week. That's the current plan. Okay. Now there may be some small amounts of work going on other times, but that's fundamentally our plan. When we get to commissioning with Beam, which won't start before January 2024. All right. At that point, we will be commissioning or doing some function of the commissioning of the machine over 3 shifts. Now, some of that could be fairly steady state sort of things. There are some things you have to do with the vacuum system and the storage ring and so forth, which are relatively steady state procedures. But the machine would be operating about 3, on the order of 3 shifts at that time. Okay.
Thank you, Jim.
Yep, absolutely.
And then the follow-up question, during that commissioning stage, how to decide which beamline will go to the commissioning or test first? Or is there any criteria or anything like that? Yeah,
so like I said, it's not just about, this is something that's important. It's not finalized as yet. Okay, I'll say there's a fundamental one, which is readiness. Beamline has to be ready. But then, of course, it also needs to be safe. Okay, so the initial phases of commissioning for any beamline include radiation surveys and so forth to make sure that, once again, the enclosure areas and everything are safe. The actual order of things will depend on readiness. If it's a complex beamline, it may take longer to get going. And I think I've seen a list of about 5 criteria that would come into this. And so we've done a draft going through that, but it's going to change over the coming months. And exactly which order things come back on is not set at this time. But we do understand fundamentally the goal is to bring as many users back to the facility as quickly as possible, and that will drive some things. Okay, so it's not set in stone yet, and it won't be until we get closer and understand better the situation with each individual beamline. That's all.
That's really good to know. Thank you, Jim.
Sure.
Okay, so let's see. For now, we don't have any open questions. So I guess you made your presentation extremely clear. And let's thank the speaker, Dr. Kerby, again. And we are going to move on to our next speaker, Marm, Dixit. You've got plenty of time, so yeah, just it's all yours.
Thank you.
Thank you.
I am gonna share my screen, which is going to be here. I'm hoping that you guys can see. Am I sharing the screen? Yes.
Very good.
Yeah, thank you. And so, hi everyone. My name is Dixit. I'm from Oak Ridge National Lab. I'm extremely honored to receive the Rosalind Franklin Young Investigator Award. This time, I'm thankful to the executive committee for giving me this honor. And I'm going to talk a little bit about my experience with synchrotrons and how I use them for solid state batteries. Before I begin, I need to thank a lot of people, Advanced Photon Source for one. They have been instrumental for the work that I've been doing in and around solid state batteries. A lot of the work that I'm going to show happened when I was with Vanderbilt University, working with Professor Kelsey Hatzel as my PhD advisor. And since then, I've moved to Oak Ridge National Lab and the Emerging and Solid State Battery Group, where I continue to leverage the APS extensively. And we also have a bunch of collaborators from all over the place that helped in doing the work that I'm going to show today. And so I'm going to start by a brief background. I'm going to switch gears a little bit from the upgrade talk that Jim gave and talk a little bit about why are we looking at batteries. Given the climate change and everything that's going on in the world, electrification is a big deal. And when it comes to transportation, getting to electrified transport can help mitigate some of these global warming challenges that we are seeing. Current lithium-ion batteries that we use essentially possess a porous electrode coupled with a liquid electrolyte and a porous anode. The issue here is we are essentially reaching the limits of performance. In the 20 years that since lithium-ion batteries have been invented, we are reaching the performance limits. And so for the next generation of energy storage, we need something that can last longer, is safer, and essentially packs more punch. And so researchers have identified that transitioning from this porous electrode to a lithium metal system can potentially provide that jump in energy density as well as safety that is needed to power and electrify the transportation sector. And essentially, that is what a solid state battery is. You replace a liquid electrolyte by a solid counterpart, and then you replace that porous anode that is graphite on the conventional lithium-ion battery to a metallic lithium. Now, however, with these systems, there are lots of issues, and the issues are cascading at multiple scales. So at all the components of the solid state battery, we are facing challenges. And the composite cathodes, we have chemomechanical degradation and three-phase boundaries. We have space charge layers and reactions at the interface of the cathode and the electrolyte. The electrolyte itself undergoes fractures and filament formation, and the lithium metal anode is unstable as well. And so we have a competing influences that govern the electrochemical performance. It is chemical, mechanical, electrochemical, all of these things combined. The bigger problem here is compared to conventional lithium-ion batteries, these things are much harder to probe because these physical processes, these processes of degradation that occur happen at physically inaccessible regions. So it's very hard to look inside and tell what's happening. And so a lot of what I did in my PhD and that I continue to do is leverage real and reciprocal space imaging at synchrotron sources and to probe these solid state batteries and try and answer some fundamental questions regarding to transport bottlenecks. What are the electrochemomechanics at play? What are the electrode transformations and interfacial kinetics that come into play? And so what essentially we want to do using these synchrotron sources and our battery materials is to understand what contributes to these transport and kinetic bottlenecks and what causes failure. And so if you take a solid electrolyte and you couple it with a couple of lithium metal anodes, if you cycle it long enough, literature has shown that we form these things called filaments. Essentially, it's lithium metal propagating through the solid electrolyte thickness. And it is not exactly clear why this happens, right? The mechanistic understanding of why it happens is not clear. And so what I was doing is we were targeting a couple of very fundamental, promising solid electrolyte alternatives and using in-situ synchrotron techniques to understand whether it is the interface, it is the microstructure, or is it the mass transport in the lithium metal anode itself that is causing these failures. And so we'll dive quickly into some results that we've gotten over the last few years. What I'm showing you here is the correlation between the centering temperature of a garnet solid electrolyte. A garnet solid electrolyte is a kind of a polycrystalline material that we can make that is a lithium ion conductor. And what we see, if you see this graph on the right, we see that as you increase the centering temperature, the ionic conductivity increases. That's the black curve here, while the critical current density decreases. Critical current density is essentially a metric of how fast you can charge or discharge the battery. And so the inverse correlation between the critical current density and the ionic conductivity was really strange to us. Ideally, something that transports ion better should also be able to transport ion faster. That was the idea, at least. And you can see that when you fail these electrolytes, you have this filament going through the thickness of the material. And so physically, there was no difference between these electrolytes, so we had to go to a synchrotron. And what we did was potentially one of the first synchrotron tomography experiments with solid electrolytes. And what we were able to show was that the sample centered at a higher temperature led to a more connected tortuous pore network that eventually led to an accelerated failure in these systems. So we did some three-dimensional modeling based on our experimental data that we generated, and we could see that the field lines across these tortuous domains were much more convoluted, and there were much stronger gradients around this that could lead to potential lithium deposition in the bulk at these higher sintering temperatures. And you can see that the bulk microstructure is more quote-unquote porous, where we have a higher X-ray transparent region that is consistent with the idea that filaments are forming within this solid electrolyte. We were also able to show a little bit of what the microstructure itself does. And so because we are able to image an entire solid electrolyte, we are able to show that there are regions within the electrolyte that have microstructures that are very distinct internally. So we have things with much different microstructure than the normal, and that leads to a transport and mechanical properties that are very disparate that causes this suboptimal regions that causes failure. Some of the other things that we studied with thiophosphate materials was understanding how these solid electrolytes undergo these profound catastrophic fractures. And so what you're seeing here are actual experimental images of solid electrolytes that we've measured through tomography. And you can see that depending on how the processing was carried out on these thiophosphate materials, these are solid electrolytes, we see very distinct failure mechanisms. But underlying these different failure mechanisms, we were able to find a unique link that essentially gave us an idea of how fracture begins in these solid electrolytes. And essentially, we were able to show that a chipping of the interface at the lithium electrolyte boundary is how these fracture mechanism begins, followed by a lateral crack growth through the thickness of the electrolyte. And so with these imaging techniques in the first half of my PhD, we were really able to show how the formation of filaments and how these solid electrolytes fail. However, the question still remains is why these solid electrolytes fail. And so what is interesting is failure is a rare event, and it is very challenging to identify exactly what is causing this failure. And so for solid electrolytes that are polycrystalline, The question we wanted to ask was what grain or what set of grains contribute to this onset of failure in these solid electrolytes. And this is where I went to 1ID, and I did an internship with the material physics and engineering group for a 6-month duration in 2020, and where we were able to individually track grains in bulk polycrystallines and track the chemomechanical responses as we cycle the electrolyte. So what you're seeing here is a schematic of high energy diffraction microscopy experiment, as well as the experimental setup. What we do is we take our sample, we put it in the beam, and we basically collect diffraction images over a range of rotation steps, and then we are able to back out the diffracting grain center of masses. We are able to extract diffracting grains orientation as well as a lattice strain. And so this is a very powerful technique that enabled us to look at an entire solid electrolyte and each grain within that solid electrolyte. So when we cycled it, these solid electrolytes in situ at the beamline, we showed a typical electrochemical response where when increasing the current density that you applied to the solid electrolyte, we see these polarization fluctuations and the impedance going to 0, which is consistent with shorting of a cell. But what was interesting to us was that the bulk grain maps did not show any stress associated with this failure. And so if you look at these two images, they are the grain maps and the hydrostatic stress of each grain plotted for the pristine sample and the failed sample. And then you can see that this average essentially remains 0. What fluctuated was in fact only the maximum and the minimum that showed some fluctuation. On average, the 30,000 grains that we imaged in a pellet showed no change. So this was fundamentally very interesting to us. So we wanted to probe what those maxima and minima are. And so when we did this diffraction microscopy experiments, we also did a simultaneous tomography measurement. So we were able to track not only the grains, we were able to track the physical microstructural properties like pores and porosity at those physical regions inside this pellets. So if you track the porosity changes between the pristine and the failed sample at a region where we did not see a straight stress hotspot, right? Where in the region where there was no microstructural, no chemomechanical response of the grain, we saw that the porosity change essentially is 0. We see no difference in the microstructure before and after failure. However, in the regions where we did see these hotspots, right, where the maximum and the minimum of the stress were identified, we saw that those local regions show a large change in porosity between the pristine and the failed sample. So this is consistent with the idea that a change in porosity is linked to formation of cracks or potentially formation of filaments within the solid electrolyte. And so this was very interesting to us. So if you track the bulk average of porosity change during cycling, you get this square plot here with marked by the solid line. But if you track the porosity changes at these hot spots and cold spots that we identify, you can see as you continuously cycle this cell, you see that they deviate more and more from this mean value of this pellet. And so it is these regions that are essentially the regions where failure is occurring. And so what did we learn so far? We learned that the change in stress state of the bulk garnet pellet is essentially non-existent. 30,000 grains, almost all 30,000 grains do not show a change in stress as you fail a cell. However, we see that the hot spot and cold spot in stress are the ones that are that we identify in the HADM are the regions that show the most microstructural changes. And so we wanted to identify what exactly it is about these regions that makes them so special, and how and why is this regions what is so special about these regions that make them high stress or low stress. And so we went back and looked at the diffraction microscopy data, and we found that while we could fit a bulk of the grains to this 220 space group of this garnet material, there was a smaller fraction of grains that we could also fit using a 230 space group. Now, these LLGO materials, the lithium, lanthanum, zirconium oxides, are strange in the sense that they stabilize in 2 cubic polymorphs. One is a lower symmetry 220 space group, and one is a 230 higher symmetry space group. In literature, people have said that the reason why you have these differences is potentially one due to cation mixing. So the idea that you replace the lithium ion with a proton, and that protonation tends to change that crystal structure from a 230 space group to a 220 space group. Cation ordering also does that, as well as effects like simple effects like just ball milling the material can lead to enough structural disorder that you reduce your symmetry from a 230 space group to a 220 space group. What people also identified, it is the 220 space group that is more conductive compared to the 230 space group. And so what we found in our systems, when the way we process them, we had a bulk of material that was in that lower symmetry 220 space group, while a small fraction of it was in that higher symmetry 230 space group. And to do that, we actually devised an experiment using a detector with a high dynamic range, and we were able to track these low structure factor peaks across the thickness of the sample. And you can see that this distinct deflection that we have, the 141 in the 230 space group, is spatially not consistent across the thickness of the pellet, and which is consistent with what we observed in HEDM, where you can see that while the blue dots are the 230 space group grains in the bulk, the location of the 220 space group grains is fairly stochastic. The reason why we think this happens is because we dope these LLGOs with a dopant material, and we cannot really control the local concentration of these dopants as we sinter these materials. And the differences in dopant concentration locally can lead to some of these differences and the formation of these two space groups that we are seeing. And so what is the implication of these space groups, right? So the question is, if we have a space group that is distinct from the bulk, what does it entail? So we took help from our modeling experts over at Purdue University, Partha Mukherjee and team, and we did some simulations at multiple length scales to understand what is the impact of these of having a domain that is essentially less conductive or with a slightly different mechanical property embedded within the matrix of a bulk material. And so on the left, you see here essentially a lithium occupation image. So we have a 60 nanometer by a 60 nanometer domain with a thin layer in between that is of a distinct phase. So we are assuming that the two outer rectangles are 220 and the middle lane here the 230 phase. So if you let the simulation run long enough, what we find is that lithium essentially gets excluded from this domain, and we only have lithium occupying the higher conductivity domains. So essentially what this means in a real system is if you have a 230 space group within a 220 matrix, that 230 space group acts as an ion blocker, and ions have to move across and around it in order to transport, and that acts as a potential barrier and a hotspot for bad stuff to happen within the electrolyte. At the mesoscale, in a 600 micron kind of domain, we see that these secondary domains with effectively different mechanical properties acts as a concentrator for stress. It also acts as a concentrator for potential when you try and run, when you apply a field through these solid electrolytes. And so through these numerical studies, we were able to show that these 230 grains, the presence of a secondary polymorph within the solid electrolytes is a giant bottleneck, both mechanically as well as for ion transport. And so far we know that we have regions of high stress and low stress within the system that correlate to regions that showed the most microstructural changes. We also showed that there is a presence of a secondary polymorph within these solid electrolytes. What we haven't shown yet is whether these two are co-located. So that's a question that we wanted to answer, whether the regions of high stress and low stress that we identify are also the regions where these secondary polymorphs are present in the solid electrolytes. And so this is what we observed, right? So if you take a cross section of the hot spot and cold spot, where these cluster of grains are essentially grains identified within the vicinity of a hotspot, these correlate extremely well to the regions where we see a high number of 230 space group grains. And so if you see the spatial mapping here, you can see that the grains identified in this blue yellow scheme are the regions, are the grains from the hotspot and the cold spot, while the grains identified as red here are the 230 space group grains. So we essentially were able to show that these two, the hotspots and the cold spots and the 230 space group grains, are highly co-located within the entire bulk. And if you look at the subsurface porosity at these different locations, we also show that these regions were the ones that show very large changes in porosity consistent with what we observed before. And so wrapping up, what I wanted to say was, using this high energy diffraction microscopy for the first time with solid electrolytes, we're able to show that these low fraction components is what dictates failures, its onset and its growth in solid electrolytes. The heterogeneity, be it of phase, be it of microstructure, be it of contacts, is what kills solid electrolytes. And we also determine using this information that we need a high degree of local control in order to process these solid electrolytes and mitigate these failure mechanisms when we move to practical solid state batteries. So these are the references that we used in this work, and I'm happy to take questions.
You, Marm, so very impressive works. And so let's see whether we have some questions. Have one question for now from Case Cheng. So I guess you can also see from
I can read it out. So he asked that he saw that we have done diffraction microscopy. Would isotropic X-ray tomography be helpful? I did not catch the dimensions on the size bar on your microstructure at hotspot, cold spots. So typically the hotspot and cold spots we identified were around the size of, let's see, they are around a few hundred microns. So this scale bar would roughly be around 10 microns. So this would be around a few hundred microns wide. And so he's asking, would it be helpful to your project to measure and visualize structure of filament as small as 1 micron minimum divergences over multiple mm? Might either of our new instrumentation enabling CM wide field of view at 0.7 micron isotropic resolution? Yeah, no, I think he has some inputs on what some tomography instruments that can be used that they have developed, and it's definitely of interest. And Keith, I can reach out to you separately for that.
Thank you, Marm. So are there any other questions from the audience? So,
I realized I went through it much faster than I was supposed to. I'm sorry.
No, I think it's good. That gives plenty of time to foster any communications. So maybe if I can ask one question.
Yeah.
I think imagine here, for example, this slide you mentioned like a pore, and the other slide you mentioned like different types of this polymorphism on different types of the space groups. Imagine if you have different types of the volume or planar disorders coexist, and so how accurate can you go to determine the microstructure? And as to some point, I have the impression you will need to make some assumption, especially if you have some presence of some very local disorder and some very large like a volume disorder. And yeah, have you tested what's the boundary there?
No, so in all essence, we got lucky with this measurement that we could pick these two out effectively, because we had a distinct reflection, and so it really depends on the it really depends on what you are trying to identify, and whether or not you can get distinct signals from the two phases in a single snapshot. Then that essentially determines whether you'll be able to capture the two phases or not. I personally am not sure of the exact limits of how fine can we go, but that's roughly the answer I have for you. I'm sorry, I'm not more specific, but I really don't know what are the limits in that sense.
Thank you, Marm. All the same. So I think you also have more questions in the Q&A session.
And so Eric Dufresne asked, I would like the experimental conditions for the diffraction microscopy. Was the X-ray dose needed to be mitigated for these battery materials? And so I think we ran this at around, I can go back and check, but this was around 70 keV monochromatic beams for both the microscopy and the tomography. We had some filters in for tomography, if I remember correctly. These materials are polycrystalline ceramics, so we didn't really do much to mitigate any X-ray dose. They did not seem to have undergone any damage while we were imaging or cycling these cells. So based on the electrochemical performance itself, we did not see any obvious need for mitigating any X-ray dose. And so that's Eric's question, and we answered that live. Reeju asked, Reeju says that the average hydrostatic stress strain was showed as 0. And so how did we calculate the D0 for the different phases? And so that's a good question. If I go back, yeah. So the D0 was chosen from essentially the lattice parameter fitting from the diffraction profiles that we got. So we fit the diffraction patterns that we obtained from these materials to identify a lattice spacing for these cubic materials, and we use that as the D0 for these phases, and that's what got used, and that's why we have this this average stress at 0.
Yeah, thank you. So I noticed there's one question labeled as answered. That's also from Dr. Case Cheng. You mentioned that they also performed a further test, and so you can take a look.
Keith also mentioned that they have tested some stuff at LBNL and ENL, but they'll be happy to help. And so yeah, I'll touch base with Keith Cheng following up.
Great. So yeah, let's see. Are there any other questions from the audience? Okay. So if not, let's thank the speaker, Marm, again, and also congratulations for the young investigator achievement. That's really impressive.
Thank you.
And so, and to our next speaker will be Dr. Amy Clarke from Colorado School of Mines, related to in-situ characterization on metallic alloys. So Amy, it will be all yours.
All right. Hopefully you can hear me okay. And let's see, are you seeing the full slideshow mode here?
Yes, I think we can hear you and we can see the full slide.
All right, and let me, okay. All right. Hi, thank you very much for the invitation to speak today. I'm going to talk about making, measuring, and modeling metallic alloys and insights that we can gain from in-situ characterization. There are a number of co-authors on this talk, basically because of the different examples I'm going to show today, but I especially want to acknowledge the students and the postdocs and also the collaborators that contributed to this work, and the different funding agencies down below that supported the examples examples I'm going to highlight today. So first, I'm going to talk about kind of where we started and then sort of get to where we are today, which is really looking at rapid solidification dynamics and additive manufacturing, in addition to linking microstructure to properties of materials. But first, I want to start with some of our early work. I'll show a few examples of multiscale prediction and control of metallic alloy solidification dynamics. And this was really focused more on conventional types of materials processing, for example, directional solidification and metallic alloy casting. And this kind of just schematically shows the workflow that we're interested in. So we really start with in-situ characterization, where we can have a metal sample, and this can vary in thickness from anywhere from, say, 100 nanometers or 100 microns, all the way up to millimeters in thickness. We then use different novel tools and unique probes like X-rays or protons or electrons, and we use them to basically interrogate our metal sample and make movies of solidification dynamics. Because we are making movies of the solidification dynamics, we're able to actually see the way that the microscopic structure and the morphology of the structures that we develop. And we're able to actually change the processing conditions on the fly if we want to try to impact the way that these structures evolve. So we are able to do controlled processing as well, and to manipulate structure development. And then really we take this dynamic information, and our aim is to really feed this into model predictions, because we ultimately want to be able to predict and control microscopic structure development from across length scales and also time scales as well. And really this coupled integration between experiments and modeling. So shown here on the top right, we have an example of synchrotron X-ray imaging of a dendritic array in an aluminum copper alloy that we've obtained. And then down below is a complementary 3D dendritic needle network modeling simulation of that array evolving sort of at the micro-mesoscale. And then on the left, we have an example of 800 MeV proton radiography that was performed of a casting mold filling at the macro scale. And this was done at Los Alamos National Laboratory's PRAD facility. And then coupled with that is a continuum scale simulation. So today I'm going to focus more on synchrotron X-ray types of results, but really I just wanted to comment that length scale is important in addition to time scale. And with regard to time scale, that becomes even more important for things where kinetics become important for scenarios like welding or additive manufacturing of materials. So I'm going to first start with an example of the type of information that we can get from these real-time synchrotron X-ray imaging experiments. So this is an aluminum copper alloy, and here we're controlling processing parameters. We're controlling G, the thermal gradient, and V, the solid liquid interface velocity. And this is for a 200 micron thick sample. And just for context, a human hair is on the order of about 100 microns in diameter. So we're talking about kind of the thickness of 2 human hairs. So here we're doing synchrotron X-ray imaging. And what you're going to see in this movie that I'm about to play is you're going to see early stage dendritic growth of an aluminum-rich dendrite in the field of view as we're pushing a planar solid liquid interface from the top down into the field of view. And that aluminum-rich dendrite is actually lower density and it's buoyant. So it's going to want to float, and you'll see it sort of get stuck upon the advancing solid liquid interface from the top down. So again, we can get a lot of interesting information about dynamics from these kinds of experiments. And one of the real benefits of synchrotron X-ray imaging in this case is that we get really great spatial resolution on the order of about a micron or so, where we can actually resolve the lamella of the eutectic microstructure that consists of 2 different phases, in this case, an aluminum-rich phase and an Al2Cu phase as well. But really the point is we can start correlating the local processing conditions and how that relates to the microscopic structure development in metallic alloys. I'm going to show one more example This is another example, in this case for melting of metallic alloy. So down below, here we have an aluminum 16 atomic percent copper alloy, and we have one of these lamellar eutectic structures. Below is solid, and here we've actually stopped a planar solid liquid interface in the field of view. Up on top is the alloy melt, and we're going to do a directional melt from the top down, and you'll see some interesting phenomena that occur. You'll see the breakup of this eutectic structure. Here, the bright phase is our aluminum rich phase, and it kind of breaks up in sort of a matchstick kind of morphology. And again, the aluminum rich phase is lower density, it's more buoyant. You see it floating off into the melt, and you see evidence of some convection in the melt as well. Taking that a step further, we actually decided to do a neat demonstration of real-time microstructure control through the development of a process-derived composite. This is now an aluminum 17 atomic percent copper sample. And so basically what we have here is a solidified eutectic, again, one of these lamellar eutectics. And what you're going to see is this melting and solidification cycling. And you'll see the way that microstructure develops and that we're able to control it. So in the previous slide, I showed you an example of that aluminum rich part of the eutectic breaking up into these matchstick fragments. Here we actually see coarsening of these particles, and they're sort of spheres and they're floating at the solid liquid interface. As we melt the interface back, we then progress the solid liquid interface forward, lock in that layered structure, and wash, rinse, repeat. We create another layer in the structure. So this just again highlights that with the benefit of being able to see the way microstructure develops, we can really have microstructural control. And again, this is just a fun example of this process-derived composite highlighting that. So if you go ahead and you open a solidification textbook, you'll find a schematic diagram like this. This is from Kurtz and Fisher. And basically our thermal gradient G and our solid liquid interface V and different combinations impact the interface stability and also the morphology of the structures that we develop with solidification. So basically we can have a planar solid liquid interface, we can have the formation of scalloped cell structures, or we can make hierarchical dendrite structures that look like trees. And basically different combinations of G and V really impact the morphology of these structures that we develop. And the aim in this work is really to, again, get this dynamic information and feed that into techniques like phase field modeling so we can predict microstructure development. And we can actually go ahead and predict a microstructure and go ahead and make it right the first time and control the way that the structure develops. So this is an example from a dilute aluminum copper alloy. So here we have 3 different snapshots from different synchrotron X-ray imaging movies. Up on top, we have a planar solid liquid interface. In the middle, we have these scalloped kinds of structures. And then down below, we have these hierarchical dendritic types of structures. And over here on the right, we have G versus V, and basically in real time, we're mapping out these different morphology regions and these growth regime transitions as well. Here, all the solid symbols correspond to bottom-up directional solidification. And one thing that was interesting to us right away is we noticed here this black line, solidification theory, would predict the transition from the planar to the cellular growth regime to be at much lower velocities than is actually seen experimentally. So that was something that was fairly interesting to us. To explore this a little bit further, what we did is we did some selected experiments that were top-down directional solidification, and then we can see these growth regime transitions shift to even higher velocities. So the question becomes why? We think this is due to convection effects, which hopefully I'll convince you of in the next slide. So with these dilute aluminum copper types of compositions, it's very hard to see contrast in the melt. So I'm going to show you an example for a tin bismuth alloy where we see things a little more clearly. This is a higher density alloy. So this is now 100 micron thick constrained sample geometry. And what you're going to see is top-down directional solidification for certain GV conditions. This has been false colored, so you'll see tin-rich dendrites sweep into the field of view from the top down. And then colored in blue, you're going to see the bismuth solute that's higher density, and you're going to see the impact of doing this top down and the impact of gravity. So here we can see the tin-rich dendrites sweeping into the field of view. We then see the bismuth solute falling in plumes. Again, the bismuth solute is higher density, and we see this enhanced effect of gravity. So why is this important? It's important because if I take this information to a modeler, convection is something that's not typically considered in modeling. So one of the benefits of these kinds of experiments is we can pull out quantitative information about what we're seeing. This is an example snapshot of dendrites from our synchrotron X-ray imaging, and we can pull out characteristics about the microstructure. For example, the primary tip radius, or the spacing of these features, the primary dendrite spacing, which could correlate to something like strength of a material, or for example, secondary dendrite arm spacing has been correlated to fatigue performance of materials. So we can pull out these quantitative characteristics. We can also do complementary 3D phase field modeling. So these are simulations that were done by our colleagues at Northeastern University of the different experimental conditions that we probed. And similarly, we can pull out quantitative information as well and sort of do this head-to-head comparison. So here we're looking at primary tip radius versus velocity. And here all the open symbols correspond to experiments, and the red and the blue correspond to simulations. So we do pretty well with respect to that. That said, if we look at primary dendrite spacing versus velocity, open points are experiments, our first simulations actually show completely the wrong trend. So why is that? When we do directional solidification, we basically start sort of snow plowing solute in front of the advancing solid liquid interface, and this creates a solutal boundary layer that we establish. And you can imagine that if we have real effects like convection in the melt, this can actually sweep away solute and affect the buildup of that solutal boundary layer. And so here what we did is we artificially truncated the solutal boundary layer. And when we go down to 100 microns, like that shown in green, we now get good matching with experiments. So I really like this example because it highlights from these dynamic kinds of experiments that we can actually start informing the physics that's missing from the modeling. And again, this is true even in these thin constrained 2D sample geometries at 100 microns or 200 microns as an example. I already showed this schematic here if you open a solidification textbook, and our early work was really this diffusion controlled regime where we're heat and solute transport dominated. That said, if you go to higher velocities, kinetics becomes important, where we lose local equilibrium at the solid liquid interface. So kinetics becomes more important for scenarios, again, like welding or additive manufacturing of materials. If I go ahead and I look at a welding textbook, I'll find a gradient that looks like this one or a graph that looks like this one on the right, which is temperature gradient versus growth rate, or G versus R. This is like the G versus V construct over here on the left. And again, we have our morphologies, our planar, cellular, or dendritic morphologies we can develop. And then this is further broken into columnar dendritic or equiax dendritic. So what we mean by that, columnar dendritic means we form these elongated kind of finger-like grains in the microstructure that can have anisotropic properties, as compared to equiax dendritic, more refined microstructures that might have more isotropic properties. And really this G over R, as we've been talking about, determines the morphology of the solidification structure, whereas the G times R, these two curves shown here, actually determine the length scale of the solidification structure. And again, we care about that from a properties point of view. So how does this apply to additive manufacturing? Much like directional solidification, we can look at these GV conditions. And here is a nice example from Ryan DeHoff and coworkers from Oak Ridge National Laboratory, And this is controlling microstructure development in Inconel 718, a nickel-based alloy built by electron beam additive. So we have here what's called the columnar to equiax transition, where again, we go from these elongated columnar grains to these more equiaxed types of grains that might have more isotropic properties. And then what we have here in these colorful sweeps are sort of the GV conditions, so the thermal gradients and the solid liquid interface velocities that are actually experienced in the melt pool. So those GV combinations are really important with respect to the location of these columnar to equiax transition kinds of curves, because that will dictate our microstructure development, even in additive manufacturing. So these are for different processing scenarios that, again, impact our GV traces in the melt pools that we experience in additive. And this is a nice example of post-mortem characterization, where this is crystallographic mapping. And simply by turning on and off the columnar to equiax transition during processing, they're able to spell out in the grain structure of the material DOE into the microstructure, which is pretty cool and a nice example of microstructural control with additive manufacturing. A more updated plot on that is this one here, which is putting the Mona Lisa in the microstructure, so sort of paint by processing. So with respect to this columnar to equiax transition, what knobs do we have available to us to impact microstructure development in additive manufacturing? So we have solidification velocity versus thermal gradient. Again, we have these CET curves, and as shown here in green, we can make some adjustments to our alloy composition, and that'll shift our CET curve. Another knob we have to turn are obviously varying the AM process parameters, or the GV conditions that are experienced in the melt pool, as shown here in red. One could imagine different GV conditions are experienced for laser powder bed fusion as compared to maybe a directed energy deposition or DED process or a wire build type of process, just as a couple of examples. So again, the location of these GV traces relative to CET matters. Another avenue that has a really big effect is adding inoculant particles to promote crystallization in the formation of refined grains. This is an active area of research right now in terms of alloy design for AM. In the interest of time, I'm not going to talk about that today, but this is an area that our group is also working on as well. I'm going to talk more about processing conditions and composition variations. So we started doing these simulated laser powder bed fusion additive manufacturing experiments at the Advanced Photon Source at Sector 32. This is an example from some of our pre-COVID experiments from 2019-2020 timeframe. So these are some of the students from Colorado School of Mines, in addition to Teresa Pollock's group at University of California, Santa Barbara. It's 5:30 a.m., so they all look pretty tired. This is the additive manufacturing simulator as shown here. And basically what this enables is us to do high-speed synchrotron X-ray imaging and diffraction of the melt pool dynamics and of the solidification process at really high spatial and temporal resolutions. This is shown schematically down here where the X-ray beam comes in. And over here, we have the location of our sample, and our sample can take a few different possible geometries. We can have a metal cross-section. We can have a metal cross-section with a powder layer on top, or we can have a packed powder layer in between glassy carbon plates. And basically the laser beam comes down, impinges on the sample, creates either a molten metal pool, a spot melt, or a raster. And then we can do real-time imaging and diffraction. And usually we're optimized for one of the two. And in our case, we're optimized for imaging. Diffraction might be something of interest if you want to look more at solid state transformations in an alloy like Ti-64, just as an example. But this is the typical type of information that we can obtain. This is an aluminum slab layer with aluminum powder on top. And here again, we have the laser interacting with the sample, and we're doing a laser track melt, simulating additive manufacturing. And we can see a lot of really interesting things going on with respect to what's happening with the powder, what's happening with the melt pool, our ability to track the solid liquid interface, directly determine solidification velocities, and again, really start pulling out quantitative information. So this is now an example of some really controlled experiments that we did. These are without a powder layer. These were done on nickel moly aluminum single crystals that were obtained from Teresa Pollock's group at UCSB that were provided to us in the form of high pedigree single crystal castings. And the benefit of this is that we were able to strategically cut out specific crystallographic orientations for these nice controlled experiments. So shown over here is an example of a typical spot melt that we have in one of these single crystal samples. We can see a lot of sloshing of the liquid metal in the melt pool, and we can see the progression of the solid liquid interface. And really the benefit is that we're able to pull out quantitative information about that solid liquid interface velocity from these kinds of experiments. So over here in the middle, we have solidification velocity versus position from the edge of the melt pool for different power conditions that we explored. And we can see some general trends that sort of fall out. At the high power conditions, overall, we tend to have lower solidification velocities. At the lower power conditions, we tend to overall have higher solidification velocities, and solidification velocity tends to increase from the bottom to the top of the melt pool. We can then couple this with post-mortem characterization. So here we're polishing into the center line of the melt pool. And we can see for the higher power conditions, in this case, we're able to retain the substrate orientation. Why is this important? If we want to create highly oriented crystals for applications like nickel-based superalloy turbine blades, we actually, in this case, want to promote anisotropy, and we want to promote the retention of the substrate as an example, orientation. We see, however, at the low power conditions that at the tops of the melt pools where the highest velocities are experienced, we tend to see new grain orientations that form. And over here on the right, if we have new orientations versus power, again, at the lower power conditions, we tend to see more new orientations sort of towards the tops of the melt pools where the higher velocities are experienced. As I mentioned, we looked at different compositions. These are a couple different alloy compositions we looked at, different single crystal orientations, different laser power conditions. And here we're looking at solidification velocity versus power. And again, as I mentioned before, we tend to see higher velocities for lower power conditions. Another thing we can look at as primary dendrite arm spacing, again, length scale of the solidification structure versus power, and some interesting things emerge out of this. We can see in particular for the high moly alloy composition at the bottom of the melt pool, as power increases, we actually tend to see more refined microstructures toward the bottom of the melt pool. So why is this? When we go to higher power conditions, we actually tend to get from a well-behaved kind of melt pool scenario to a keyholing regime. And when we have a keyholing regime, like that shown here over in the right in our radiography, we actually end up with a keyhole collapse. We form a void that's present there. And when that keyhole collapses, we experience a very high velocity at that point in time. If we go ahead and we zoom in and do post-mortem characterization, we can see at the location where that keyhole collapses, where the high velocity is experienced, that we actually have new grain orientations that form. So this suggests that these high velocities, we trigger the columnar to equiax transition and the formation of these new grain orientations. So we not only can understand the way microstructure develops, we can understand the formation of defects as well from these kinds of experiments. So what can we do with this type of information? Some of our early analytical modeling was comparing these columnar to equiax transition predictions to our experiments for these single crystals. So these are two different examples of velocity and gradient and these CET predictions for different alloys and different crystal orientations. And a couple things became clear to us right away. The first is that I should mention too, the colorful part here, again, are these GV traces experienced in the melt pool for the different power conditions. And then these are our CET extrapolations. The first thing that became clear to us is we need more sophisticated modeling to get better thermal gradients. So importantly, from these real-time experiments, we get the solidification velocities that we can directly measure, but we have to model the thermal gradients. We also needed more data at higher velocities, and this is something that we're currently working on as well. And then also these analytical types of models have some fudge factors built in them. For example, this N0 is nucleation site density. And here we're using an approximation available from Inconel 718 from the work of Andrew Polonsky at UCSB, but really this has to be calibrated for different alloy systems. So there's a lot to really go into this to start becoming predictive. And we kind of took a step back from this to start thinking about how could we do better modeling, especially to get those better velocities and those better thermal gradients so we can start doing more informed modeling. So in addition, one thing that we wanted to better understand was sort of the ground truth of the melt pool shapes as compared to what we get in 2D with our synchrotron radiography compared to the actual 3D melt pool shape. So this is work we're doing in collaboration with Teresa Pollock's group at UCSB, where we're using tri-beam to actually look at the 3D melt pools that we looked at with synchrotron X-rays at the APS. So over here on the left is a well-behaved melt pool where again, we can see solid liquid interface velocity. Looking top down, we see these elongated columnar grains that extend from the edge of the melt pool kind of inward in this case. Here we're actually able to use the tri-beam data to make a fusion line point cloud and to convert this to a surface and really have full crystallographic information in 3D about the grain structures we developed. Why do we care about this? We want to, again, compare this to what we see in 2D, and then we want to use this to compare to our modeling that we're doing as well. One interesting thing about this particular data set is we saw this halo of grains present kind of at the melt pool edge, and then again, these columnar grains that kind of emanate from that, which I'll talk about here in a second. But again, the important point is we get the 3D melt pool shape. So here we're now directly comparing some flow 3D simulations. So these are multi-physics simulations that include conduction and convection. And we're directly comparing that to our radiography that we got. So here we have solidification velocity versus solidification time, and we're comparing flow 3D versus the radiography. And this gives us a benchmark to compare those velocities to make sure that the modeling is matching the experiments. Here, we're also comparing the characteristics of the melt pool. We have length versus melt pool dimension for the width and the thickness and the depth. Here, we're comparing our flow 3D simulations to our radiography, in addition to our 3D tri-beam to just 2D SEM. And we see we do a really nice job with width and thickness of the melt pool. So again, that shape of the melt pool has to match in our simulations. Depth is a little more off. This is associated, we believe, with our experiments that we did at the APS and sort of sample alignment and things like that. So there's a little more wiggle room in the depth. But nonetheless, now we can one-to-one ground what we're seeing experimentally with the modeling. And now we feel confident that we can, now that we have matching velocities and melt pool characteristics, we can go ahead and get the thermal gradients. So these are example thermal gradients that we've obtained from Flow 3D. So here we have solidification velocities locally in the melt pool as compared to what Flow 3D gives us. We also went and calculated the thermal gradients another way by using the velocity and the cooling rate experienced, and the results are shown here. So we're currently refining, I guess I'll say, the thermal gradients that we get, and then armed with these GV conditions, now we're in a position where we can go back and do more of the analytical modeling. We can also take those process model results and we can start feeding that into phase field, for example, to predict microstructure development under rapid solidification conditions. I want to go back to this interesting example that we saw from our tri-beam data set, where we recall that we had this halo of grains and these columnar grains emanating sort of from the halo sort of inward. And now we understand from Flow3D the local temperatures that are experienced in the melt pool. And one thing that was of a concern to us is the explanation for these grains. It doesn't seem like they come from columnar to equiax transition. And so we went and we took a look at recrystallization as being a possibility. So in the literature, we found some recrystallization data for pure nickel. And it turns out on heating, sort of at the fusion line in the heat affected zone, we reach temperatures that are sufficient that could drive recrystallization right at the fusion line at the heat affected zone. We believe that this is driven by when we actually prep these samples for APS, we grind these samples. And so there's some strain in the sample, and when we hit it with a laser, it was enough to actually cause recrystallization. And then we see that epitaxial growth from that halo of grains in this particular example. That's actually the thing responsible for those surface new grains that we see, in this case, not columnar to equiax transition. So we really have to be careful about what we're seeing and really getting that right, I'll say. Another thing we can get from the tri-beam, for example, are geometrically necessary dislocation densities that tell us about the local dislocation contents. This is an example from the UCSB group where we did some APS experiments with them as well on a cobalt nickel alloy, the designing 4AM. And here we can see again, nice 3D representation of all these grains. And then this will be coupled back to the synchrotron work that we're doing and also the modeling as well. And we can really start understanding a lot about what's driving the microstructure evolution during additive manufacturing. So going back to these microstructure processing maps, we know we need some improved models. So looking back at an example spot melt, where again, we can track the solidification velocity. Here we have velocity versus time for a low power, well-behaved melt pool, and different velocities for different crystal orientations that we looked at. We can go and do the post-mortem characterization as shown here. And if we look, in this case, we're actually looking at these little dashed black boxes here. This is really at the melt pool edge. We see our planar zone that then transitions to our columnar dendritic zone. And clearly in both cases, we have a dendritic microstructure that exists after these solidification experiments. If we go and we think about that in the context of existing solidification models, and we do some sort of traditional classic types of predictions, it would predict that we actually would have reestablished a planar interface. And clearly we see still the presence of dendrites. So if we look at our fully dendritic microstructure shown here in blue for our maximum velocities experienced, we know that we still have dendrites beyond what's predicted with classical theory. So this suggests there are other things we have to start incorporating into the modeling, things like kinetic effects that are going to be really important moving forward to do predictions for rapid solidification scenarios. And this is some example work that we've been doing with my colleague Alen Karma at Northeastern University, where we're doing a quantitative phase field modeling to predict rapid solidification dynamics and microstructure evolution. So this is the first quantitative model that actually predicts microstructures that we see predicted from theory, even at very high solidification velocities. In this case, on the order of 1 to 2 meters per second in aluminum copper. We're comparing this to another experimental technique that we do with Lawrence Livermore National Laboratory called dynamic transmission electron microscopy, where we hit a sample with a laser and we're able to watch solidification at 1 to 2 meters per second. And in this case, we form some banded microstructures that we see that are predicted. And we're able to quantitatively predict that. So now, armed with this new model applicable to rapid solidification, these GV conditions that we can get from our process simulations, we're now in a position where we can start doing predictive microstructure modeling. So I'm going to switch gears a little bit and talk about Ti-64, which is a ubiquitous titanium alloy and the influence of scan strategy. So here we're looking at electron beam powder bed fusion for different spot melt scan strategies, our random spot melt, and then de Hoff, which is kind of also a spot melt scan strategy, but kind of lies in between random and a traditional raster scan strategy. So down below, we have as-built microstructures And we can see that for random, we tend to form more colony alpha plus beta microstructures. And at faster cooling rates, we tend to form more alpha prime martensite types of microstructures in the as-built condition. So one thing that we did is we started looking at the as-built texture as a function of build height and scan strategy. So this was done with neutron diffraction at Los Alamos National Laboratory. Basically, we had slit scans that we did up the build height. And here we're comparing the random and de Hoff spot melt scan strategies as compared to the raster. And it becomes pretty clear that we don't see a lot of texture development from the bottom of the build to the top of the build, but we do see a difference based upon scan strategy. The spot melt strategies look different than the raster. We also then compared this to large scale electron backscatter diffraction that we did in collaboration with NIST here in Colorado up in Boulder. So there's a lot going on this slide. I'm just going to highlight some important points. I'm going to use the bounding condition of our random spot melt scan strategy and our raster. And what we can do is we can look at the as-built microstructure. We can then apply the orientation relationship and back calculate the high temperature beta microstructure as shown above here. So here we have the beta microstructural condition for the random spot melt scan strategy and the raster scan strategy. We can then put that in the context of our GB map. So here, if we look at random and the Hoff, the green and the blue, we actually see that we live sort of crossed in this mixed microstructure regime. And if we look at the high temperature beta condition, just after solidification, we see a mixed microstructure. Where if we look at the raster condition, the red, we tend to be more on the columnar side of things. And again, we see these elongated columnar grains. We also were able to relate this to the as-built microstructures that we see. And we notice from the different texture components that if we have increased texture on the 1,1 bar 2,0 type of plane, like that shown here at the equator, we tend to see more diffusionless microstructures. Whereas if we have increased texture on the 0,1 bar 1,2 at the 45, we tend to see more diffusional microstructures. Why is this important? We're selecting different alpha tie variants in additive. We're able to basically screen for, or it suggests we can screen the as-built condition. And by doing that, we're able to sort of back calculate all the way up to the as solidified microstructure and really know a lot about our microstructural state. And this was regardless of type of build process, whether it was powder bed or DED, directed energy deposition kinds of processes. So this suggests that the texture components in the as-built condition could be used to potentially qualify and certify the microstructural condition for TIE 6.4. Similarly, we did some larger length scale. This is a wire DED build that we did with Sandia National Laboratory that they provided for us. And here we actually see an atypical microstructure, these large alpha beta colonies at a build pause where we actually see cracking that was present in the build. This is again back calculating the beta tie high temperature condition. And then we were able to rationalize the crack path propagation pathway based on the different slip systems that we have in TIE 6.4, which was pretty neat as well. So now that we're armed with all this nice crystallographic texture information from neutron and large scale EBSD, we want to start linking that to mechanical properties. So we pulled some mini tensils at 0, 45, and 90 degrees to the build. And here are some example mechanical property results that we've acquired. We're currently working with VTT in Finland and also Los Alamos National Lab to try to forward model with crystal plasticity the mechanical performance of these AM builds. We're also looking with computed tomography at the defects that we see and correlating that again to the mechanical properties as well. So this is an active ongoing area for us. So one of the bummers about TIE 6.4 is that we actually have the solid state phase transformation to deal with. So more cleanly to look at solidification, we've been looking at metastable beta tie. This is TIE 1023. Basically that high temperature beta tie phase we can retain at room temperature. So here are some synchrotron X-ray spot melts that we have from some of our TIE 1023 experiments. Here we're directly comparing that to our modeling again. Here we have cis weld, which is more simplistic and is a conduction only model, as compared to flow 3D, which is multi-physics, which is conduction plus convection. Again, this becomes really important as we go to high power conditions where more keyholing is experienced. We actually have to go to a multi-physics kind of model. We can then use this information to inform these columnar to equiax kinds of predictions and rationalize the microstructures that we see. One of the neat things about TI 1023 is that if we have the retained metastable beta phase at room temperature, if we were to deform it, we have the potential to undergo transformation-induced plasticity, or TRIP, of the metastable phase to martensite with deformation. So here's an example of one of our laser track melts that we looked at APS, and we can see this massive heat affected zone right below the laser track melt where we have martensite formation that occurs. So this is pretty neat because it suggests during the laser track melt, we actually are accommodating the residual stress during the build, and it suggests that these types of beta TI alloys might be more forgiving in terms of the AM build process. And there's really more to understand here in terms of which grains tend to transform and what are the local conditions. And that's something we're currently looking at. So the last example I'll highlight is now going to the mechanical properties of TI 1023. This is actually on wrought processed material now. In addition to transformation-induced plasticity, when we cool from the high temperature and we retain the beta phase, we also form an omega phase, that's an athermal phase, and that can evolve with aging. So shown here is stress versus strain, and we can see in blue our as quench condition. If we age these microstructures, we get this massive increase in yield strength over 4 times, and we're also able to have good ductility as well. So again, summarized here, a massive increase in strength while retaining good ductility. And this is due to the combined effect of the omega phase in the microstructure in concert with the transformation-induced plasticity, or TRIP. There is a point at which we overage the microstructure and we end up forming a different mechanism of dislocation channeling that we see. Shown here is some postmortem microscopy where clearly we have transformation of martensite with deformation. And this kind of just summarizes the state of the art in terms of these metastable TI microstructures that we can generate with different deformation mechanisms that are active. For example, we can have the alpha and beta plus slip. We can have beta plus omega and trip, and then we can even add alpha phase back into the microstructure to enhance the strength a little bit. And so a lot of things can be done to manage the phase stability in the microstructures that we get. In this particular work, we actually were more interested in the dynamic properties of these materials. We were interested in absorbed energy for protective structures for DoD kinds of applications. So we pursued doing some Kolsky pressure bar testing at the APS, which is schematically shown here. This is a little penny as compared to some of our tensile samples. And down below, we can actually see, this is an example for a cobalt chrome nickel high entropy alloy that undergoes twinning induced plasticity, but we can see the gauge length being ripped apart, and we can actually see evolution of the microstructure. From these experiments, we can get the diffraction data as well, in addition to the stress strain response. So this is now an example for our TI 1023, the as quench condition, strained at 1,000 per second while we're doing real-time diffraction. Shown here in black is our stress strain response, and it has a funny shape just because of the ringing that's experienced during the test. We see in blue the matrix phase decreasing, commensurate with the increase in the formation of martensite, so evidence for TRIP in the microstructure. From the imaging, we can get information about the extent of necking and the elongation. And then we can do postmortem analysis, and clearly with crystallographic mapping, we're seeing the formation of martensite. And then work we're doing more recently is rationalizing the different mechanisms that we see that are present, and whether we have the potential for TRIP, for example, in a hard or a soft grain orientation. Aging these microstructures impacts the propensity to undergo transformation-induced plasticity. So that's something to consider as well. And then the last slide I'll show is an example of phase stability and TI moly. These are also beta TI alloys. TI 12 moly actually undergoes TRIP and twinning induced plasticity in the microstructure, whereas TI 15 moly is twinning-induced plasticity alloy, so it undergoes twinning. We can look at quasi-static deformation, our results at 1,000 per second. We can see from the diffraction data, Ti-15 and Ti-moly, we go from sort of spots to rings, suggesting that we have grain size refinement. Unfortunately, in this case, in the Ti-12 moly, we don't actually see or capture the evidence of the trip also happening in the microstructure. But if we go and look at post-mortem microscopy, clearly we see the formation of martensite in the microstructure with deformation. And then our Ti-15 moly clearly undergoes twinning-induced plasticity. Looking a little more closely at the Ti-12 moly with transmission electron microscopy and a focused ion beam fib foils, this little region here, we actually see the twinning happening, and we actually see the martensite formation forming within these twins, which is pretty interesting. And then similarly, the box here, we see a lot of this very refined microstructure evolution that's happening, that's kind of hierarchical at really small length scale. So really this combination of trip and twip gives us this benefit of good elongation and improved properties for high rate response. So in summary, state-of-the-art characterization is allowing us to study solidification dynamics, including under AM conditions. Obviously, the processing conditions we use drive microstructure and defect development. We can obtain velocities and thermal gradients from experiments and modeling, combine this with postmortem characterization, solidification theory that'll ultimately allow us to predict and control microstructure development during advanced manufacturing. A lot of opportunity exists to design alloys, for example, with metastable phases, like I showed for the Ti-1023, matched to AM processing in particular. I didn't talk about inoculation today. Crystallographic markers can show insight into the microstructure condition produced by additive, and maybe can be used for qualification and certification in the example of Ti-64. And then in-situ diffraction during high strain rate loading allows us to identify the active deformation mechanisms and to design novel alloying, the phase stability or metastability, processing pathways, and also microstructures and properties for performance in extreme environments. And so with that, I'd like to thank a lot of the different funding agencies that contributed to this work, and I'll stop right there and invite any questions that you might have.
Thank you, Amy. So that's really extremely impressive and informative presentation. So from the audience, if there are any questions, please feel free to just type in the Q&A session. You certainly cover a lot of different topics. Any questions from the audience? Feel free to type in the Q&A. And meanwhile, I feel I have a tons of the questions. Maybe I will start from some simple ones.
Sure.
First, I think first you mentioned the part during this melting pool. There's the formation of the halo of the grains. Why it's not a 2D surface but a 1D ring to form from the grain? I thought if you have the melted part and the not part, they should appear as the whole boundary. It seems that.
Yeah, so the halo that we're seeing. So yeah, what we think happened there actually is that we believe that, and in fact, you can see here, you can actually see our grinding layer, like when we make these thin 100 micron, 200 micron thick cross sections for the APS experiments, we grind front to back and then on the top as well. And here we actually have ground the microstructure. And so that allows you to have the strain present in the material that when we hit it with the laser in this example, we actually end up basically in the heat affected zone and at the fusion line, having that recrystallization happen right there. Oops, sorry, my computer's going wonky here. We actually are able to form that halo of the grains, and it's kind of happening at the top surface there where we have that deformation layer. And then we see the epitaxial growth of some of those grains at the top, like into the, or at the top across the melt pool surface. if we had columnar to equiax transition, we would expect to see subgrains down, penetrating down more into the melt pool, right? And so that was a flag to us that in this particular case, we don't necessarily have the columnar to equiax transition. And we have to be really careful about that in the different melt pools that we're analyzing. And in other melt pools, we actually don't see this sort of recrystallization thing that we see in this one particular example. But again, we want to be very thoughtful about when we have CET or not, and we really need to look at the microstructures in more detail to really confirm that kind of a finding.
Thank you. So I think there are a few questions from the Q&A session.
Sure. I'm not sure if I'm able to see those here. So
Would you like to read that loud?
let me exit out of here and then I should be able to see the questions. Sorry, stop sharing the chat Q&A. Oops, nope, I'm still not able to see that for some reason. I'm not sure why.
So yeah, let me then try to read and you can answer with your slides.
Okay, perfect, sounds good.
Great. I think the first question from Eric to friends. How do you plan to use the new features of the APS plus U in your research?
The upgrade, yeah. So one thing I didn't talk about at all, which is another active area that we work in, is refractory alloys and high density alloys, right? And so you can imagine, so even in the nickel-based alloys and the cobalt nickel alloys that I showed, we're looking at very thin cross sections of material, right? Ultimately, we want to be able to understand things like refractories as well. And let me see if I have a nice example of something like that. So this is an example of additive manufacturing and the CET kind of modeling in a refractory alloy. And so we really want to be able to understand higher density alloys. And I think the upgrade will help us to be able to do those kinds of high density materials that are very challenging, right? For us currently. So that's one area. There's a big interest in developing these refractory alloys, multi-principal element alloys or high entropy alloys for ultra high temperature applications, for defense applications above temperatures of 1200 C that can survive extreme environments. And so I think the upgrade will help us to be able to do those kinds of refractory, high Z kinds of materials. Also, there might be some benefits in terms of looking at things like nucleation. I didn't really talk about that today either, but this is an example of dynamic transmission electron microscopy, where we're able to look at smaller length scales and time scales. This is nucleation off an oxide particle in melt. And I think that with upgrades, maybe there's always the opportunity to push to smaller length scales and faster times. So nucleation is really the holy grail. And the more we can do that, the more we can understand the microstructure development as well. So that's another thing. I also think with the upgrade, maybe there's going to be more sort of zoom in, zoom out. I'll call it sort of like Google Maps, right? Where we can actually look at big length scale, small length scale, those kinds of things. So I think there's a lot of really neat opportunity going forward with the upgrades that are happening at the APS for these kinds of experiments. So hopefully that answers that question.
Thank you, Amy. So here there's one more question from Gary and Navrosky. So for Amy, is your in your video of a single crystal nickel moly aluminum later spout melting, there is a downward propagating void, termed like a black sphere, moving through the solid. That is perplexing.
Oh, sorry, could you repeat that one?
Right. So in your video and showing like a later spout melting for this nickel moly aluminum.
Yeah.
Yeah, it seems to be a downward propagating void.
Oh, yes. Yeah. The keyhole
that?
that we experience, yeah. So this right here, this dark region here, I'm guessing. Yeah, so these are the voids that we form. Basically, when we have keyholing, we actually form with higher power conditions, sort of a more narrow, deeper melt pool. And we end up with that keyhole that collapses. And when that collapses, we end up forming these voids or pores in the microstructure that are retained as a defect structure. And so you need to be cognizant when you're doing the AM processing about developing these keyhole kind of structures, because that'll be a defect, right, during the AM build. And so when that keyhole collapses, that's where we get that very high velocity and those new grains that also form as well. But yeah, these are voids that are retained in the microstructure for high power conditions when we have this keyholing mode that we get when the keyhole collapses.
Thank you. Thank you, Amy. So have no other questions. So maybe I can ask you one more minute to ask one. You mentioned that this full simulation, you can also get convection.
Mhm.
Any condition that you see that convection also be like with similar significant portion and comparing to this conduction. I think for this metal alloy, maybe to some conduction is always like a dominant. Right now, it seems like the power only increase a little bit at the same order of magnitude. And do you see that as a convection dominant already, or what's going on there?
Yeah, the conduction is definitely important, and Sisweld, which is conduction only, does a reasonable job for sort of well-behaved melt pools, like these little nice shallow ones shown here and shown here over at low power conditions, right? You can also do analytical solidification modeling as well, like Rosenthal modeling. Again, that works pretty well for some well-behaved melt pools. But when we get to those higher power conditions where we experience that keyholing, that's when the melt pools are more turbulent and the convection piece becomes more important. And you really need to go to the multi-physics modeling in order to capture that convection part as well, because just the melt pools are more turbulent and less well behaved. So you really need to go to Flow 3D to capture things like the keyholing, to capture the enhanced turbulence, I'll say, in the melt pool. And we find that we do need to do that for the high power conditions. We have to go to the actual conduction and convection modeling, not just conduction, if that makes sense.
Thank you, Amy. So, let's see, we don't have further questions here. And with that, let's thank the speaker, Amy Clarke, again. And so we'll have a 10 minutes break from now, and we'll come back about 3:10 in Central Time. So if you are in Eastern Time, that will be 4:10, and I will see you in 10 minutes. We'll keep having more plenary sessions. Thank you very much.
Thank you. Take care.
Thank you. Hello, everyone. So now it's 3:10 Central Time, and welcome back. So our plenary session will keep going. So our next speaker will be Dr. Christopher Murray from University of Pennsylvania. He will be introducing us about the progress on the artificial atoms based on the self-assembled crystals. Christopher, it will be all yours.
That sounds great. So, and I'll just share presentation, make sure this works all right. Is my audio okay on your end?
Your audio is perfect.
Excellent. All right. Host has spotlighted your video for everyone. Okay. So at the moment, are you folks seeing my slides?
Seeing your slides and not in a full screen mode.
Okay, let me take care of that right now. All right. So hopefully that's now in full screen mode.
Yes.
Great. All right, great. Well, thank you, everyone. It's been an exciting day. I really appreciated being included in the program to understand more of the upgrades and the incredible undertaking that is ahead of you all this coming year. So I'm Chris Murray. I'm a materials chemist. I am in the Department of Chemistry and in Material Science here at the University of Pennsylvania. But it's a particular honor to be included because the research of my team and the community of materials researchers that focus on nanoscale systems is extremely dependent / grateful for the tremendous capabilities that the Department of Energy makes available through its facilities. In fact, I will share with you today a little bit of the work that we do in that regard, but we benefit from research that is carried out around the globe. So some at Grenoble, some at Soleil, some at the Swiss Light Source, but in particular, Argonne and Brookhaven, and to a lesser extent, Oak Ridge have all been essential in the progress in our area. So that I guess also motivates me to just congratulate the folks that are taking on this tremendous task for the upgrade, because it sounds like the capabilities and the increased stability that will offer to a global scientific community is really going to be remarkable. So in the title, I often use this little catch phrase at the first, building with artificial atoms. And that is the underlying theme of the work that my team has been pushing for many years now, that synthetic chemical methods to make uniform nanoscale objects are advancing in such a way that we start to have the hope that we can think of using them as replacements for nature's own building set in the periodic table, or at least an extension of the options for design. I will present a number of things that relate to sort of colloidal chemistry as depicted by this little cartoon. We will take advantage of a number of the kinds of capabilities that Argonne and the user community have been advancing through their efforts in terms of the characterization of the building blocks. But most of my time will be focused on ideas about self-organization and the emerging frontier in terms of the development of new materials that are engineered on the mesoscopic scale. So from nanoscale building blocks coupled together over hundreds of nanometers to microns up towards macroscopic films and so on, but that capture some of the unique size-dependent and unusual combinations of size-dependent properties in these systems. At the bottom of the slide, you kind of hate to do this, where you say, this is what I'm not going to talk about, but I do want to acknowledge. So because of the kinds of capabilities that are supported at Argonne and its sister facilities, the centers for the nano centers, and also at Brookhaven, much of my group's activities in the area of development of new concepts and model heterogeneous catalysis would be impossible without strong collaborative partnerships using a variety of different types of scattering techniques, but in particular, the unique insights that come from X-ray absorption, both ex situ and in situ. But in order to keep a slightly more coherent, or less incoherent theme for what I'll share with you today, I won't talk much about the catalytic work. We will try to mix a little bit of the hard and soft work on this piece. And this is a slide of my group. It's now a few years old, pre-pandemic, but actually I thought as I was clicking through for a more up-to-date one, I realized that since I'm integrating over the contributions over a number of years, it actually is appropriate to point out some of the work that you'll see, and I'll call out individuals as we go. But our dendrimer team with David and Catherine Elbert, some of the superparticle assembly with work by Yao Ting, some of the efforts that we are doing in terms of some of the rare earth chemistry and some of the microfluidics, all team members are sort of represented here. And this is a panel of some of the overall support that we've received over the years, but I will slip back just for a moment to say that the most significant new thrusts are being supported by three primary entities for this topic in my group: the Office of Naval Research, the NSF through its continued support of Penn's MERSEC, and in particular, some of the most exciting new ideas on photonics and other types of nanocrystal-based optoelectronic materials is part of a large multi-investigator effort, an STC center led from the University of Washington called IMOD, and you'll see a lot more exciting stuff from that program as we go. All right, so within our tool set, we rely on a variety of different types of techniques for solution phase, nucleation and growth control. This is a classic story in this mode, and I won't spend more time on that piece, but I would only emphasize that there is an extremely wide span of materials that now can be accessed and manipulated using some of the techniques based on these types of solvothermal methods. And what I'm showing at this moment with this slide is this idea that, again, we've been promoting for a number of years, that you can begin to think of an alternate sort of analog of the periodic table when you begin thinking about the members of that new library of building blocks being defined not just by composition, but by dimensionality, geometry in terms of sizes and shapes. The members of that much expanded periodic table, if they can be produced with sufficient uniformity, control of surface structure, facet expression, and the like, give us a really powerful tool, we believe, to take the concepts of chemistry, self-organization, coupling and overlap of electronic orbitals, but to play that out on the mesoscopic scale. And so when we think about that periodic table, that library, whether it's for applications in the areas of optics or thermal and electrical properties, or as I mentioned, catalysis, I also will not speak at any extended length about the work that we do on magnetism, although magnetic studies also benefit greatly from a number of the capabilities that are offered in the beamlines and the communities of experts in that area, magnetic circular dichroism, and a variety of spectroscopies, again, that really help us to understand more about the underlying origin of interesting magnetic behavior. All right, so we're going to try in this piece to exploit that nanocrystal periodic table. We're going to innovate in some dimensions on the synthesis, helping to make a number of new systems that have been tailored and now can be deployed as part of this nanoscale building block set. We're going to talk about assembly using a variety of techniques, from thin film deposition, interfacial assembly processes, and some microfluidic, processes, systems that point towards ideas about more three-dimensional encapsulation and control of the self-assembly process. And then we'll point to some of the interesting properties that come from the interactions between these effects. So coupling between the nanocrystals or the nanocrystals and the microscale geometries will be highlighted as we get further along in this presentation. So for those who maybe have been following this field for a few years now, we've seen some of the early entrants in the ideas of using semiconductor nanocrystals, often also referred to as quantum dots, as initially laboratory curiosities, understanding fundamental physical properties of scaling of electronic behavior as you approach sort of molecular limits. But those types of insights from the early 90s have translated over the subsequent decades, 2 decades, with the work of extremely bright and motivated engineering teams, both in academia and in industry in particular, to see a translation of those building blocks now as part of the display technology that you can choose to take advantage of if you stop by Best Buy or your favorite electronics store, right? So the work that I'll talk about today, you should keep in mind that the methods, the high temperature solvothermal methods that are used to make these types of structures have in some specific examples already been scaled to sort of ton scale production, and that they underpin a big value add in a very large investment in technologies, including both optically pumped enhanced LCD type technologies, which have been out in the market and doing well for a number of years now, but in particular, a very a close transition with products already available in some parts of Asia, but a very large shift in the industry with direct electrically pumped quantum dot enabled systems alongside organic LEDs and other technologies, and actually even in some cases hybrids of these. And so these were isolated quantum dots in the first part, optically accessed, not electrically integrated. The most recent examples involve dense close packed films of the quantum dots that allow enhanced charge transport and communication. And so those will mirror a couple of the things that we'll talk about in our time here together. All right, sorry, apologize, a little touchy when you're doing this presentation from this mode. All right, so one of the things I'd like to mention as we follow that theme of building blocks towards electronic and optoelectronic devices, in particular, this is work done together with Sherry Kagan and her team, is the idea that one can take these types of nanocrystal components and through careful choice of their size and shape and composition, but also the coupling between those components by manipulation of the surface chemistry, you can produce a family of semiconducting films which have a unique set of properties in that they show the hallmarks of band-like transport, delocalized electronic transport, even though the individual constituents are still composed of somewhat discrete components, now just talking to each other through their overlap of their quantum confined energy levels. And this process of engineering the surface chemistry is really critical to get the right strength of coupling to be able to take advantage of that artificial periodic table that we were talking about. And so I wanted to mention some experiments that we actually did carry out at Argonne with the assistance of some of the great teams at your site. And so in this case, we were looking at this exchange process, which is critical to activating the electronic transport in these films. But one of the challenges is to be able to actually watch or understand the kinetic processes as well as the mechanical response as the spacings between these particles is modified. And so in this particular experiment, we were able to do an in situ grazing incidence X-ray experiment in which we introduced a new competitive ligand below the layer of the assembled quantum dot films. This happens to be a 2-component quantum dot film. We'll talk more about that a little later. But in this case, one could follow through the real-time X-ray process to understand the dependence of temperature and time and other critical variables, and also to understand what rates of exchange were optimal to avoid mechanical stresses and cracking and other types of negative processes that can occur during this type of exchange. And so, again, this is only possible when one has the good fortune to be a user of a facility like Argonne's and the APS's expertise, as well as their infrastructure, to be able to look at real-time exchange processes, doing chemistry on the nanoscale, but in an interface layer that's just one particle thick to help us to understand the exchange process. But when that exchange is done thoughtfully, and I will apologize, I'll just go to the next slide for time, but we can begin to build, and this in particular is led by Sherry Kagan and her team, from the nanocrystal based films, these artificial atoms assembled together, we can start building out analogs of all of the key components in microelectronics to make different types of solution processable devices that have performance that greatly exceeds the best of breed organic semiconductors and starts to eat into the low end of a number of classic inorganic polycrystalline semiconductors in terms of their performance characteristics. These types of systems can be played out by depositing these nanocrystal films over wafers up to about 4 inches, and then you can really begin to start characterizing prevalence of defects, reliability, measuring the mobility of the devices or performance characteristics across many positions on the supports. It helps, if we can take those artificial atoms from the nanoscale constituents and build them up to wafer size assemblies that then still retain some of the interesting tunability of the smaller components, then we're getting closer to our goals. And I will mention also that we are quite interested, it's not the focus of this talk, but in methods of manufacturing that do scale the deposition and manipulation of these systems. These happen to be some images captured by, again, grazing incidence diffraction studies, but deposited over wafers by a robotic dip coating process. So this is a coating process which has the potential to be more useful for reliability and large-scale deposition for the development of these types of systems. When we think about the analogs for what we can do with atomic systems and traditional semiconductors, one of the great challenges in the area of nanoscale science is to have concepts that provide an analog to doping. Doping is a very powerful strategy for modifying electronic and optical properties and conventional materials. And if you have all the tools of nanoscale size and shape tuning, but you had to give up completely the strategies of doping, I don't think you'd feel that you got the best part of that exchange. In this particular example, what we're showing here is the idea that you can organize these artificial atoms into extended arrays, and then by choosing a particle of a different composition, but controlling its shape and its surface treatment so that it basically can fit optimally on the lattice sites of the majority phase, we can start to develop systems that have a combination of periodicity within the lattice, but also the introduction of new centers for electronic charge introduction or for optical properties. Happens to be plasmonic gold in this particular case. But the key here is that we have a strategy now for the introduction of materials of different compositions that helps to separate the organization and the assembly from the underlying inorganic nanostructures geometry. And in this piece, we have an example here where the surface chemistry is being modified with different types of supramolecular ligands, so dendrimeric and other related constructs, so that you can begin putting together systems. In this particular case, it was putting square pegs in round holes, but basically you can use the organic chemistry and the interactions between the head groups to anchor the materials and the tail groups to control their organization, so that you can begin to have design freedom in terms of the geometries and sizes of these structures. All right. When we think about putting our artificial atoms together, one of the classic strategies for getting multi-component properties was the co-assembly or co-crystallization. And some of this work actually began in a much earlier generation. Some of the expertise, Elena Shevchenko, who now is at the Nano Center at Argonne, actually helped to pioneer much of our efforts to control phase stability, and we've continued to expand on the set of two-component systems. But in this strategy, one has the opportunity now to put together complementary material components on nanometer length scales, and then with sub-nanometer gaps, you can fuse these particles to turn on strong interactions, exchange coupling, or electronic phenomena such as electronic transport or energy transfer processes that are your new degrees of freedom to engineer different types of responses. And I will note that the types of packing arrangements that can come from these systems can get increasingly complicated. They're not limited just to very simple expressions of crystal organization. This happens to be sort of a classic mathematical representation of tiling, small rhombi trihexagonal tiling, but you can see the relatively high degree of symmetry that is reflected in some of these colloidal assemblies. But this is still a crystalline system. There is although it's a rather complicated primitive unit cell, it is a crystalline system. I would note that in a number of these systems, we've also, together with both Elena and Dmitry Tilapin and my former students, Xingchen Yu and Jun Chen, we began and continued in our separate ways to study quasi-crystalline behavior in these systems. So maybe I'll give a slightly bigger picture here. But these systems can adopt both crystalline arrangements as well as quasi-crystalline arrangements. In this case, the individual particles, now our artificial atoms, are grouping together in clusters. Those clusters make the shaped elements, the tilings, if you will, that then allow us to express a number of classic sort of Penrose tiling type implementations for systems that have rotational symmetry, but not translational symmetry. So in that type of work, we have the possibility to do more exploration of systems that have combinations of crystallinity at the nanoscale and aperiodic behavior at the mesoscale. All right. When I think about the frontier of putting together different pieces, and we've been working towards this goal over a number of years, you'll see a few examples, but the idea of taking these nanoscale building blocks and being able to control the directional interaction in these systems So using shape of the particles and their complementary geometry and faceting really as a surrogate for bonding, for the valence that we would think of in nature's atomic building set. And in this particular example, it's a combination of rods and spheres that are co-assembled to give a binary lattice, locking in place in the small void that is created by the faceting between the rods, a position for each of those spheres. You can see a missing one down here that sort of shows you, that there's still some level of defect structure in these systems. But as we increase the complexity of the geometries, as we begin to control faceting and angles to grow out families of materials, these happen to be rare earth phosphors. They're of interest in a number of nonlinear optical applications, as well as certain of the members of the family have some very interesting magnetic properties because of their high spin rare earth constituents. But in these systems, you can begin to think about designing materials that really start to assemble themselves with complex complementary geometries. So if you want to think about this, this is sort of puzzle pieces or boxes of Lego that when you dump them out on the lab bench, they begin to organize themselves. Actually, usually you dump them out on as liquid, giving them the degrees of freedom to move around until evaporation or other stimuli help them to lock into place. But this allows us to start thinking about much more complicated assemblies. And I know I have to be careful on time, but I do want to tip my hat a little bit to the idea that two worlds can meet in this space where hard materials, physical properties from the nanoscale inorganic constituents can be married with different types of supramolecular recognition chemistry and assembly, basically taking advantage of a number of custom ligands to control the particle-particle interaction and even the density and expression of the ligands on those systems. So in our own teams, we've been lucky to have talented folks that took on the challenge of developing families of ligands that could begin to build out these supramolecular structures, in this case, a dendrimeric system, through multiple generations that now allow us to control density, cone angle, the softness of the interparticle interactions as we organize the systems. And so you can see here in a generation 2 dendrimer where there's quite close packing possible because the ligands are not that bulky yet. But by the time you get to G4, generation 4 in the branching, now you have a much more open framework which the particles can adopt with the spaces that you see here in the electron micrographs in between them not being empty space, but now occupied by the organic subphase of the dendrimeric material, which is actually a significant portion at this point of the total volume. So as we begin to use those types of assembly strategies, then we can start to differentiate the binding of those ligands on different parts of our systems. We can grow different types of heterostructures, so we make the inorganic more complicated while getting an expression of the different components of the organic. Now we have systems that are inherently surface active. They orient with polar groups on one end and non-polar groups on the other. So these will begin to organize both as membranes with a high degree of orientational order, or even into three-dimensional crystals, as shown in this example, where now you have a system which has magnetic and metallic, magnetic oxide and metallic functions encoded into the inorganic and then oriented by the organization of the systems. All right. Now I know that I'm right in my time for a transition, so I'm just going to mention one other theme, because the idea of this three-dimensional assembly, I think, is an important part as we look to the future of where some of the colloidal nanocrystal advances are going to come. So growing different types of three-dimensional assemblies, supercrystals, if you will, or superparticles comprised of those artificial building blocks, is where a number of new opportunities arise. In this particular example, we are using a microfluidic approach. Hopefully on the right-hand side, you can perhaps see some of these superparticles which are being extruded through an orifice. And as they travel up, they shrink, losing some of their solvent in the interior to the exterior, and they begin to shrink down to sort of micron scale. But these systems can be made uniform enough. And if I go just a little bit further, pardon me, they can be made uniform enough in their composition and their overall geometry that they become the next level of building block for the organization of colloidal matter. The systems that we're looking at here, again, benefit tremendously from a number of, let's see if I can speed this guy up. So this is real-time X-ray data that's being taken, small angle scattering at Brookhaven National Labs during the growth of these supercrystals. You can see the development of some of the ring structure as we begin to see crystallization occurring. This type of insight in terms of the dynamics and what ultimately allowed us to understand more about the mechanistic aspects of the growth of these supercrystals was only possible because of the opportunity to observe the growth process in situ, in real time, while the materials were being generated and modified by their solution conditions. And as I point to these multi-component now superstructures, which are on the order of a system for sort of hundreds of nanometers up to micron scale, then we have the opportunity to begin to make Janus structures when the constituents that make up the particles don't like each other and want to be excluded, or core shell when they want to be excluded, but the one phase likes the interface. So you can make, again, systems that have encoded now on dimensions that are relevant for a number of optical phenomena. You can encode chemical composition, modulation, and a variety of opportunities in terms of the design. Now I'm going to see, I was worried a little bit with that last piece. If it, oh, okay, it's still gone. All right, so this is an assembly now of these superparticles. Sorry, now it catches up. I pushed the button a little too fast there. I'll go back. So in these designs, we have the opportunity to organize those superparticles into an ordered array. So atoms into nanoparticles, nanoparticles into superstructures, the superstructures then sufficiently monodispersed to become the building blocks of colloidal matter reaching up to the micron scale and macroscopic length scales. And that means that you can capture interesting physical properties at each stage as you go through the system. And I will close with one example of that interesting property, if it allows me. We'll have to skip the extra X-ray scattering. All right, so the systems here can incorporate 1, 2, or 3 components in their properties, but because of the superstructures dimensions being close to the wavelength of light, a whole host of interference effects modifying the emissive properties of the constituent nanoparticles can begin to be exploited. And in particular, for these systems, it's possible to produce these systems where you have micro lasers. So each one of these systems has emissive particles assembled into a system where there are optical modes, whispering gallery modes, that allow a concentration of the light field in at the periphery of the particle. And these systems then begin to have a nonlinear response and emission so that you can begin to see amplified emission from these materials. And if we think about these building blocks, they can also begin to show coupled modes. So in the image above you, or sorry, in front of you, you see a single particle, a monomer, and then dimer, trimer, tetramer, and so on. The images that you see are now the overlapping resonant light fields from each of the superparticle systems that makes up those components. And they have distinct optical signatures that are a result of that coupling and the interference between those modes. The extension of that with those superparticles is that you can begin to play games, and this is together with Sherry Kagan and her team, that allow you to manipulate the output, a power-dependent output for these lasers. So they're switchable in their optical properties between red and green and other, depending on the choice of the material. But here it's because we have a process in which at low fluence, you are not yet filling all of the trap states, or basically filling a number of emissive states at higher pump rates. You begin to emit from higher energy levels because the lower lying levels are no longer available for occupation and for the participation in the resonance. And so with these systems, now you have the possibility of generating a number of bright, very spectrally narrow emitters that you can organize and assemble on optical length scales for these pieces. All right, I know I've pushed the limit in terms of my time. I want to thank you all for your attention, and I'll take any quick questions. But I just want to say again that the work that we do would just be impossible without a collection of the Department of Energy's user facilities, and more importantly, very strong and productive collaborations with the scientists at each of the locations where we bring our projects. We never fail to benefit from the experience of the research teams we interact with as we execute on our user plans. So thank you very much for your time. I know it's going to be a tough year ahead, but fantastic things at the end of this upgrade in terms of new capabilities and new science.
Thank you, Christopher. That's extremely exciting research. I think we still have some 2-3 minutes for all the audience to have any questions. Feel free to type in directly in the Q&A session. So while any audience are typing in, I have one question, probably a general question, and because its design space is very large, and so how do you see future to explore a little bigger area and on the design space? And in particular, it seems is there possibility to do a priori this predictive design to get to know some function with this kind of large number?
Yes, so that's an excellent question. And I think that really is the frontier, both in terms of how we automate some of the experiments to be able to provide data that will improve the theory and the prediction component. But what your question goes to the heart of advances. Many of the projects that we're involved in have extremely valuable collaborations on different types of theoretical with different types of theoretical contributions, including molecular dynamics work together with Sharon Glotzer and her team at the University of Michigan. Also, in terms of some of the assembly work and prediction of organization and properties with Alfons van Bladeren and Marjolein Dijkstra at the University of Utrecht. In work to date, the theory contribution has helped us to understand the experimental work, and in some exciting examples, help to anticipate or narrow our experimental focus areas, and that's extremely valuable. But as your question noted, the experimental space is so huge, that periodic table, what should we be combining, and what would be the implications with surface control and so on? I think theory is going to play an extremely important part in helping us to make better choices of what we should do, rather than just focusing on what we can, proof of concept of what we can do at the moment. And I think one of the earlier presentations today noted some aspects of experimentation and some work on robotics and other parts. For experimentalists to reach out with a sufficient density of data to properly and effectively engage the theory community, I think some of those bridging technologies are going to be very, very important. I think that is the secret for experimentalists to be able to provide enough of the appropriate parameters that our computational colleagues can then tune their understanding of their models and come back with even more powerful predictions.
Wonderful. Thank you, Christopher. So great answer. And so it gets the presentation is self-explanatory. We have no other questions. And so I think with that, that's everyone to thank the speaker again. And we'll move on to the next speaker from Reeju, Pokharel from Los Alamos. She will be talking about the machine learning and materials characterization.
Very good. Thank you again, folks.
Thank you.
Hello?
Hello? Yeah.
Sorry, my computer just locked me out, kicked me out.
I just saw you 1 minute ago. So yeah. Good.
I'm sorry. Can you see my slides?
Yes, I can hear you and see your slides.
Great.
Wonderful.
Okay. Hello, everyone, and thank you for the introduction and the invitation to speak today. So I've been using APS for more than 10 years now, and starting from my graduate school days, and have done lots of beam times. But today I'll be switching gears and won't be talking about any of the experiments that I've done at APS, but I'll try to explore how we can see how we can leverage machine learning to optimize these one-off experiments at light sources, with a focus on 3D mesoscale imaging of materials dynamics. And our previous speakers, especially Amy, gave us a very nice and comprehensive overview of why that's important. But so I'll just give a very brief motivation on that. So to understand materials dynamics, we need to consider various length scales. So at the atomistic level, we see arrangement of atoms, crystal structures, and voids and defects that are within angstroms to tens of nanometer range. And at the other side of the spectrum lies this macro scale regime, which involves bulk samples and engineering components that are larger than millimeters. And nestled between these two regimes is the mesoscale, which is the least understood among the three regimes. And this intermediate regime features emergent behaviors, defects and interfaces, and their complex interactions. And through the knowledge that we've gained over the past several decades, we now understand that the behavior within this mesoscale regime plays a significant role controlling and influencing macroscale properties. So, sorry. So in addition to characterizing the features in the mesoscale regime, we also want to observe the materials dynamics across a broad range of timescales, so going from all the way from nanoseconds to tens of seconds, and in some cases even hours, months, and years. So this allows us to examine phenomena such as phase transitions, phase stability, kinetics of all these things happening, damage nucleation, and all the way up to solidification and microstructure development during manufacturing and aging. And despite these goals, we still can't perform these multi-scale measurements at both relevant time scales on a single sample. And this is pretty much our grand challenge, as these measurements are crucial for developing and validating multi-scale models for bridging both the length and time scales that spans several orders of magnitude. So thanks to facilities like APS, we now have sophisticated techniques that can enable us to investigate 3D mesoscale materials across multiple length scales. However, obtaining detailed 3D microstructural imaging of a polycrystalline materials is still a challenge and requires hours for a single state measurements. So one of the reasons for this, which we'll focus on today's talk, is the widespread use of brute force algorithms, which demand redundant information to be measured to invert the observed 2D detector images, and then those redundant images are then used to extract 3D microstructural data. Therefore, going from these raw diffraction patterns to microstructures can take sometimes days, weeks, or even months in some cases. So this slow data inversion process also hinders real-time feedback during experiments, making it challenging to identify and focus on regions of interest within a given experiment. And this constraint significantly restricts our ability to conduct informed multi-scale experiments targeting materials dynamics across various length and time scales. So while we can collect a few 3D states during a beam time at different resolution, our ultimate goal is to reduce the data requirement and the analysis time, allowing us to zero in on regions of interest and employ multiple techniques for doing multi-scale measurements. And even worse, without real-time feedback, we remain in the dark sometimes regarding the quality and usefulness of the terabytes of data that we take home, only to maybe potentially discover weeks, months, or even years later that we should have approached the experiments slightly differently. So with that as a motivation, here's the outline for today's presentation. So first, I'll highlight some of the topics that I'll discuss. So here are some of the topics I will discuss. So I will begin by exploring how we could use machine learning to reconstruct crystal orientations from diffraction data. And then I will show how to adaptively tune our ML models for improved predictions, and then briefly touch upon the benefits of incorporating physics knowledge for developing more robust surrogate ML models for real-time feedback with an overarching goal to enable these multi-scale materials characterization experiments at beamlines. So reconstructing microstructure from a diffraction pattern is an inverse problem. So to illustrate this, I will begin with a very straightforward example of EBSD. Although a light source isn't required for EBSD characterization, it is the most commonly used characterization technique for crystallographic microstructure analysis, and is relevant to other synchron-based methods as well that I will discuss later. So in EBSD, our primary goal is to determine the crystal orientation that is responsible for this observed diffraction pattern on the detector. So at a specific location, we get a diffraction pattern, and by rastering through our sample space, we can collect these diffraction images from all the locations. So these images are then reconstructed to get these crystallographic orientation maps. So for a sample, say, divided into these n by n grid, we need to collect n square detector images. And while this is still a nonlinear inversion, the reconstruction process, this one-to-one mapping between the input diffraction pattern and the corresponding crystal structure. So this is one of the simpler problem that we decided to tackle. And I'll show you later when we're talking about HEDM, this problem becomes a very high dimensional nonlinear problem. So to address this problem, we developed a very straightforward convolutional neural network. So the model takes diffraction images as inputs and outputs the corresponding crystal orientations represented by quaternions. And ideally, training such a network would require an extensive training data sets covering the entire parameter space, and acquiring such a data set using measurements alone is very impractical. So as a initial training step, we generated 300,000 simulated diffraction patterns from cubic symmetry orientation space with 1.5 degree disorientations using this EMSoft software that was developed by Professor Mark DeGraaf's group at CMU. And we trained our CNN network, and we knew that the simulation trained network would struggle with the experimental pattern because the experimental patterns will have inherent noise in the images, and also the forward model that we use to generate these synthetic images will have missing physics. So because of this discrepancies, the experimental pattern would not these simulated trained network would not produce high accuracy reconstruction. So to address this, we retrain some of the weights of the CNN layers using only 1,000 experimental pattern, and then use these retrained network for reconstructing the experimental data. So here's just an example showing the differences between the experimental diffraction pattern and the simulated diffraction pattern for a given orientation. And you can see that the simulation pattern has pretty much very similar features as the experiment, but you see distinct differences in local intensities. And if we were to feed these experimental image directly to our synthetic data set trained network, it would generate a very low accuracy predictions. But after retraining the network, so here are the red dots here. I hope you can see that are the 1,000 training set that we used to retrain some of the weights of the network. And now the network has learned these local differences in the images, and this misorientation map is calculated as the difference between the ground truth orientation and the CNN predictions, where you can see that the low values corresponds to very high accuracy reconstructions. And this the distribution here on the right shows is for the validation set. So these are these grains that have never been seen by the network, and it shows that the misorientation is within 98% of the 98% within 10 degrees misorientation. And the map here in the middle shows the this deviation of the quaternion norm from unity. And in the absence of ground truth, where we have to know the ground truth to calculate these misorientation map, you can see that as this map shows very similar features as the misorientation map. So in the absence of ground truth, you can use this as a metric to glean the accuracy of your reconstructions. And one thing to note is that these ML models are instantaneous, and you can reconstruct these full 2D maps pretty much instantaneously. And this approach can be extended to various material systems and different instrument parameters. And in this case, and you can also start incorporating known physics, in this case, the disorientation between two crystals. And also, we know that the quaternions have to have unit norms. So in the previous case, we did not include any of these information, but now we can make a custom loss function and include all of these known physics to improve the accuracy of these models. And so the idea behind this approach, this on-the-fly retraining approach, is to develop a model architecture and train a base model before conducting any experiments. And then using a small number of experimental patterns, you can quickly retrain some of the model parameters on the fly to account for the changes in the material systems or instrument parameters or other factors. And this enables faster microstructure reconstruction for us to provide feedback during experiments. And so the other thing we wanted to look at was the level of noise in the experimental patterns. How bad can it be for us to still be able to reconstruct the diffraction pattern accurately? So usually the pattern quality degrades due to defect generation and when or imposed deformation. But here we have emulated that scenario by changing the exposure time used for collecting each EBSD pattern. So typically 30 millisecond is used for EBSD data collection for a fully annealed sample, and the pattern becomes noisier with decreasing exposure time. And although the microscope itself can operate at 1 millisecond frame rate, conventional software tends to produce noise when reconstructing these diffraction. So here's an example of the same microstructure using these 30 milliseconds diffraction pattern versus this 1 millisecond diffraction patterns. So we developed a deep learning model to automatically denoise our experimental data. So here again, the top row shows the diffraction patterns collected from the same location in the sample with different exposure times, and the bottom row displays the denoised image using the trained ML model, showing its ability to extract information from even these very noisy, even the noisiest image. So this pretty much appears to be complete noise to a human eye. So this shows that by incorporating these ML tools in our experiments, we can collect data faster. So in this case, maybe we instead of counting for 30 milliseconds, we could just count for 2 or 3 milliseconds and get almost an order of magnitude faster measurements. So now we have extended this approach used in EBSD for Laue diffraction, and this is an ongoing collaboration with Dimitri and group at HPCAT. And here are some preliminary results on only synthetic data to reconstruct crystal orientations from Laue pattern. And here I'm just showing you an example comparisons. So here's the crystal orientations represented as quaternions. The color, the XYZ are the 3 quaternion components, and the color is the Q0, the scalar component of the quaternions. And this is the predictions made by the CNN, and this is the error between the ground truth and the prediction. And since so in this particular framework, we learn both the inverse and the forward model. So we can also predict the Laue pattern from the predicted quaternions. And here I'm showing you the ground truth Laue patterns and the predicted pattern from these from our model. And you can see that in this difference plot, the prediction, the ML does a very good job in predicting these Laue diffraction patterns. So this is ongoing work, and we are in the process of applying this to experimental data and see what will need to be changed when we go from synthetic to experimental data. So although neural networks offer fast inference, it's important to understand that they are also only approximations, and these approximation can be used as initial guesses to significantly reduce the search space. So for example, in this case, we have used the ML2 for coherent 3D coherent diffraction data analysis. And in this case, we develop a CNN network which feeds in these 3D diffraction patterns, and we present our object, the crystal, as spherical harmonics coefficients, and then that's our those are the inputs to our model. So these spherical harmonics coefficients that describe the shape of this object and the diffraction pattern. And then we train our network, and then once trained, the network, given a 3D diffraction pattern, it predicts the spherical harmonics coefficients. And then we go one more step where we iteratively tweak these spherical harmonics coefficient to further optimize using this method called extremum seeking to adjust these shape to get a better prediction of our measured and predicted diffraction patterns. So here are some example comparisons between the ground truth and the ML predictions, and you can see that the this CNN combined with the adaptive feedback approach accurately predict these very complex shapes, even though the training set had more smooth shapes involved. These test sets were obtained from experimentally measured crystals, so it had from a polycrystal, so it had a very complex shapes, and the predictions was able to predict both the shape and the phase fields and displacement fields inside these crystals. So in the next example of adaptive ML, we developed a encoder decoder type 3D CNN network to map this 3D diffraction pattern or intensity to the phase and amplitude of the 3D electron density. So in this case, the diffraction pattern are represented as this low dimensional objects in the latent space, and so which is this bottleneck in the encoder decoder architecture, and this latent space is then adaptively tuned using this extremum seeking method, allowing us to improve the predictions of our work. So you can now, instead of so if your images are 2K by 2K, now instead of actually having to tweak a 2K by 2K space, you only have to tweak this low dimensional space, and in this case just the 2-dimensional space, so you can really quickly start getting reconstructions in real time. So here's just an example where we're starting with this 3D grain and moving through this latent space. You can continuously deform both the shapes and the phase field inside these crystals. And here's an example showing the ES algorithm tracking the electron density of this time-varying state of this object based only on a continuous match of the measured CDI intensities. So the top most row here shows the evolution of the tracked object and its phase field going from state 0 all the way to state 90. And the second row from the top here shows the voxels that have changed in density and phase value at these subsequent states relative to this initial state. And clearly you can see that the object has changed a large amount by the final state, where the difference between the voxels are themselves an object almost the same size as the original object. So, and the third row here shows the states created by this adaptive tracking, which are generated by moving in this low dimensional latent space. And this fourth row shows just the voxels whose phase difference between the tracked and the tracking object exceed greater than is greater than 0.5 degree radians. And this shows that the tracking is highly accurate at reconstructing this changing object throughout this dynamic evolution. So the implication of this result is that during an in-situ experiment, this approach can be to allow for real-time tracking of a grain evolution. And all of these right now are demonstrated only on simulated data, but we are collaborating with Ross Harder at Sector 34 IDC to extend these approaches for experimental data reconstructions. So the final technique that I will talk about today, where we aim to apply these ML tools, is to accelerate the high energy X-ray diffraction microscopy data reconstructions, which is extremely challenging because the 3D microstructure characterization techniques requires solving high dimensional inverse problems. So in the case of EBSC, you saw that there was for each crystal, there was a corresponding detector image. But in this case, now we have to map these 2K by 2K and N projections, which is the rotation angles, to this 3D microstructure, which in this case 512 by 512 by N layers, and with 2 microns or better spatial resolution. So as an initial attempt to tackle this problem, we represented this high dimensional detector images as a few principal components, which were then used as inputs to predict the full field orientation distribution in a single calculation. And here's an example results for the simulated data where the CNN prediction. So the column here on the right is the CNN predictions, and the column here on the left is the ground truth for the three different Euler angles. And you can see that the model does a decent job in, it's not perfect, but it does a decent job in reconstructing the spatially resolved microstructure. So in the second step, instead of compressing the diffraction pattern using the linear transformation like PCAs, we instead use neural network itself for this nonlinear compression of the data into the reduced space. And this reduced latent space in this case is only two-dimensional, and it was adaptively tuned to obtain the microstructure map that best matched the observed diffraction patterns. So, and as I mentioned earlier, since this latent space is only 2D instead of 2K by 2K by, say, 360, the tuning takes only several seconds, which is several orders of magnitude faster than the brute force approach that is employed for orientation reconstruction in HEDM data. So here's one example. So in this case, we predicted both the crystal orientation and the elastic strain field components. So the top row here corresponds to the ground truth values. So I'm only showing you the one of the Euler angles, the epsilon1 and epsilon6 components of the elastic strain tensor. This the column here corresponds to the CNN predictions, and then the second column here corresponds to the CNN prediction combined with this adaptive tuning. And you can see that the error has significantly reduced after using this optimization process, and that's true for both orientations and the elastic strain field. Okay, so again, the implication of this work is that all of these tools can be now integrated to work together, providing real-time feedback for enabling multi-scale measurements to examine materials dynamics at different length scales. So here's just one example of a vision for multi-scale 3D imaging, where you would image the 3D evolution of a microstructure and under deformation, say, and as the deformation progresses, you can zoom in on the regions of interest, say location of stress concentration inside a single grain, and then further image that region using high resolution imaging technique to look at dislocations being generated or cracks are being formed, to really have the understanding of a different phenomena, or in this case, maybe plastic deformation and damage in materials. So for the rest of the time I will quickly talk about how we can develop surrogate ML models for direct numerical simulations to further help provide real-time feedback during experiments. So it's proof of concept work. We developed a network. It was a simple dense network to predict the crystal reorientation at a single strain step. So we generated synthetic data, synthetic microstructure, 3D microstructure data using Dream 3D, and performed a deformation simulation using EVP, FFT, or elastoviscoplastic full capacity simulations, and those data set were used for training our neural network model. And we once trained on the simulated data, we applied the simulation trained network to the experimentally measured microstructure data. So one thing to note is, in this case, this was one of the first times us developing these tools. So we manually generated a local 3D regions to feed into our model, instead of using CNN network, which actually takes into account the spatial interactions. So anyway, the simulation trained network was then used for predicting the experimentally measured microstructure data using this. The data was collected using HEDM, and you can see that again, I'm plotting the misorientation between the ground truth and the predictions, and for different strain levels, and you can see a reasonable reasonable accuracy of our surrogate model. And here's just a 2D spatially resolved plot, misorientation plot extracted from these 3D volumes. And even though the Dream 3D produce synthetic data have like equiax grains and random texture, the model was able to accurately predict reorientations even in a complex morphology of measured HEDM data. Similarly, this surrogate model was then extended to predict not only crystal reorientation, also micromechanical fields, and at multiple strain steps. So here, here's an example of a. So in this case, we decided to use the 3D convolutional neural network architecture with a recursive inputs and outputs to predict both microstructure and micromechanical fields evolution. And again, we used EVPFFT simulations for our training. And once trained, we got a so when comparing to the EVPFFT simulations, which took about 1300 seconds to simulate deformation up to 6% strain on an 8 processor, while this surrogate model took only about 3 seconds on a single processor, which is a multiple orders of magnitude faster. So we can really use these surrogate models during our experiments, because running these direct numerical simulations most of the times requires large number of CPUs or HPC clusters. So here I'm just showing the comparison between the EVPFFT simulation and the surrogate model predictions of the average von Mises stress evolution with strain, and also the 2D bin histogram of the principal stresses to look at the yield surface evolution from the EVPFFT and the surrogate model. And this shows that the model is able to reasonably predict this macroscopic material response just based on the microscale training data that we provided it. So in the next few slides, I'll show you the spatially resolved strain and stress fields comparison between the surrogate model and the EVPFFT simulations. So here I'm plotting the strain tensor component just along the loading direction for one of the middle slices from the 3D microstructure. And you can see that the top row is from the direct numerical simulation, and the second row is the predictions from the surrogate model. And the model is able to capture these local structural details and hotspots formation that's predicted by these EVPFFT model. And so since the neural networks give approximate values at each strain step, the error tend to grow from one step to the next when using the previous predicted state to predict the next state. And this can be seen from this plot here on the right, where I'm showing the average difference between the EVPFFT and the surrogate model. And you can see that both the error bars and which are the standard deviation calculated from the error distribution tend to grow with increasing strain. I'm showing you the plastic strain component. Again, you can see that the model does a real job in capturing these local hotspots and also the stress fields. And again, the same results where we see the model able to capture these local hotspots in the micromechanical field evolution. And in this case, the error that accumulates at 6% is around like 10%. So here I'm plotting the distributions of quaternion norm on the left, and the divergence of the stress fields at the on the right at different strain levels. And we know that the predicted orientations need to have unit norm, and also the predicted stresses must satisfy equilibrium conditions. But from these histograms, we can see that on average, the model learns that the norm must be 1 and the divergence has to be 0. But this non-zero standard deviation indicate that these constraints are not always satisfied by these models. And the fidelity of these models can be further improved by maybe directly incorporating some of these physics constraints in the model. So we can build these ML-based surrogates using just the data-driven approach that I just showed earlier by minimizing the error between the ground truth and the predictions, or we know the physics, then we can start adding those as soft constraints. So say if we know that our stress, we need to satisfy the stress equilibrium conditions, so we can impose this divergence of the stress field to be 0 as one of the components in our loss functions. Or the other way to do it is actually putting this known physics directly into the network architecture to ensure that these physics laws are always satisfied. So in the next couple slides, I will just show an example of incorporating Maxwell's equations as hard constraints in the CNN network for predicting beam dynamics. And in this case, the inputs are the current densities and the current density and the charge densities, and the outputs are the vector and the scalar potentials. And by construct, the electric and the magnetic field that comes out of this network satisfies the Maxwell's equation. And here are 2 slices from the 3D beam distribution to compare the data-driven, the PIN, and the PCNN approach that I talked about. And you can see that, so here's just a slice. Error. So I'm looking at the divergence of the magnetic field, and so the data-driven approach has the highest error. The PIN has does a better job than the data-driven approach, but when we impose this constraint directly into our architecture, now we have we certainly adhere to these constraints all the time, and this is just summation over the full volume, and you can see that the data-driven approach is much worse than the other ones. Okay, so here's just a summary schematic showing the overarching vision of how we could leverage these ML techniques for doing more informed experiments to capture mesoscale materials dynamics, and maybe incorporating some of these known physics in our ML models for micro reconstruction would help us build these robust ML models, which would be able to generalize beyond the training set, and we could be using it during our experiments to do these multi-scale time resolve experiments. With that, I'll just stop here. Thank you.
Thank you, Reeju, for very interesting presentation, seeing so many very recent results. So for the audience, if there are any questions, please just directly type in the Q&A session. And we still have a few minutes to ask your questions. And while all the audience are typing, I'm actually having one question related to what you show actually here on this microstructure reconstruction.
Oh, sorry.
It's materials independent, right? Which means that you can abstract the materials into a few parameters. So it should be applying to all kinds of materials, or is there any kind of limitation, like a different crystal type, to do this reconstruction?
I mean, yeah, you theoretically, yes, it should be possible to do different crystal structures at once, but in practice, I think it's a little bit harder. So using these, so most of the things that I showed is we start with the base model that is for say for cubic or hexagonal, right? And then we build our model, and then we so I was showing those latent space tuning part, right? If you know that you have various parameters that could change, right? Like, so your crystal structure could change, your lattice parameter could change, your instrument parameters could change. So you could set up your latent space based on this knowledge that you already know about your system. And then once you have that base model trained on maybe cubic or hexagonal, then you can quickly retrain it for, not a retrain, but, you know, adaptively tune your network for given crystal structure. Or you could, I mean, you could make a general model by having lots and lots of data sets from different material systems, different structures, and all, but I think doing it adaptively is a more reasonable, computationally reasonable way of doing it.
Thank you. It's good to know. Okay, let's see. So I guess it's also very clear. And as of now, we don't see any questions. I think without other questions, so let's thank our speaker, Reeju, again. And
Thank you.
Thank you. So I think we'll soon to move on to the very last presentation for the day. And Brian will use there. Yeah. Great.
Yep.
Great.
I'm here.
Oh, yes. We'll be talking about also nanomaterials.
Yeah. I'll be talking about some synthesis mostly. Let me try to share my screen here. Let's see. All right. Can you see that?
Yes.
Okay, great. All right, so my talk is going to be mostly some synthesis, and so when I was thinking about what I wanted to talk about, we've been doing a lot of work kind of lately, last, I don't know, 5 or 6 years, really thinking about nanocrystals, quantum dots that have optical properties or optically responsive in the infrared. So all the way from the edge of the visible out to the far infrared. So this is a TEM image of a little field of mercury telluride nanocrystals. And then on the right is an image using a camera, an infrared image of one of my students' faces using his nanocrystals. So that's mercury telluride. And broader theme of what I'm going to talk about really are ligands and the role of ligands in a few different ways and how important they are to making these nanocrystals with this wide range of optical properties. So starting with silicon, I'm really going to talk about 3 different materials: silicon, germanium, and mercury telluride. And they all have some of their unique aspects related to the ligand chemistry. And with silicon, which is a system we've been working on in my lab for over 20 years now, thinking about how to make quantum dots with controlled optical properties, size-dependent properties, you really need a reactant that you can decompose into the material. So if we're thinking about silicon, something like a silane or something like that, we're doing most of our growth in solution and in solvents, and so a reactant that will decompose in the solvent and do that in the presence of a capping ligand or some sort of organic molecule that can stick to the surface of the material. Okay, so this is a real challenge for silicon, and there are a couple of ways that we've sort of come around to dealing with the surface chemistry of silicon and being able to do the controlled growth of the quantum dots, and in some cases control the shape and make nanorods and nanowires. We have really 2 different approaches that we use in my group. One is this approach on the left, which is kind of a colloidal workaround, as I like to think about it. And it was developed by Colin Hessel when he was a PhD student in John Vino's group at the University of Alberta. And Colin worked in my group as a postdoc for a few years and kind of taught us how to do this. And it's a really nice way to make silicon quantum dots of controlled size. You take silicon suboxide, hydrogen silsesquioxane, HSQ, decompose that in a furnace under reducing environment, and at high temperature above about 1100 C, you get silicon oxygen disproportionation, and you crystallize silicon quantum dots in an SO2 matrix. And this works really well. You can make nanocrystals that are small, below 2 nanometers in diameter, all the way up to like 50 nanometers in diameter. And you make these quantum dots, you etch the oxide away, and you're left with in solution hydrogen terminated silicon, which then you passivate with some sort of alkene. And so you can do a thermal hydrosilation, for example, on that. Another way to actually do a colloidal synthesis is to use metal seed particles. So on the right, I have an example of silicon nanorods made using tin as seeds, using trisilane as a reactant in a high boiling solvent like squalane, and doing that in the presence of tin. Tin has some solubility for silicon at relatively low temperatures, around 200 C or so. And the silicon will dissolve into the tin and then crystallize out in the form of these nanowires. And for this reaction with the nanorods, usually we use something like dodecylamine as kind of a weak capping ligand to just stabilize the rods as they're produced. So those are two different examples of capping ligands. In the case of silicon, if we want to have fluorescent material, we want to prevent oxidation of the surface. And so you need to have a strong capping ligand. And so this alkene forms a silicon carbon bond, which is great for stabilizing the nanocrystals. But the reason it's difficult to do this in solution, one reason is that silicon carbon bond is not reversible. So once you form the silicon carbon bond, it won't come off, it won't detach. But these silicon nanocrystals, once you make them, are really quite stable, relatively monodispersed. You can control the peak of the photoluminescence all the way from the band edge of silicon. So silicon's band gap's 1.1 eV. So in that near infrared range, like a little over 1100 nanometers, all the way into the green. So trying to push the emission down into blue. I've given talks about this, just, you know, what is the blue light emitting silicon? And silicon suboxide can emit blue light, and it can be actually fairly bright, but it's not size tunable. And it's very, very difficult to stabilize extremely small nanocrystals that really should emit blue. So usually that smallest wavelength for emission for silicon is about green, about 520, 550 nanometers. You can make pretty bright nanocrystals, so quantum yields up around 30% or so. And so one application of these that we've been looking at is for biological imaging. And the reason is, well, one of the reasons is the silicon light emission is in this kind of optical window for biological tissue. So you have these windows of transparency for optical tissue and water. And so silicon emits in that range. That what's shown here is a kind of NIR1 or near infrared 2 region, kind of in there. So that's interesting. There are other materials that can emit in that range, but like cadmium selenide, which is one of the more common, commercially available fluorophores for biological imaging, doesn't emit in that range. So silicon emits in the near infrared, and it's also non-toxic, so it's biocompatible. And those are two positive things about silicon. But the one drawback with silicon is that its light absorption near the band edge is really weak. So silicon's an indirect band gap semiconductor, so its absorption coefficient is really low near the band edge. So the emission can be, say, 800 nanometers, but the light absorption is actually really weak there. And so usually when we do photoluminescence spectroscopy, emission spectroscopy, we'll photoexcite at about 400 nanometers. It's not because the material doesn't absorb out at 600 nanometers or so, but the density of states is low and the light absorption is weak. So for doing biological imaging work, you usually need to photoexcite in the blue. So even though your emission is in the red and the near infrared, which is good, that need to photoexcite in the blue is a bit of a drawback. So if you're doing, and I'll talk about how we get around that in a little bit. So when you're doing work in biological systems, you need quantum dots that disperse in aqueous media. So you can't just take, you know, undecanoic or not undecanoic acid, that's what we're using here, but undecanoate, and putting that onto the nanocrystal and having hydrophobic particles, undecene. So you need a hydrophilic group at the end. What we discovered is that small silicon nanocrystals can actually be hydrosylated at room temperature using a bifunctional ligand with an alkene at one end and a polar group at the other end. So something like a carboxylate, for example, or an ester actually works even better. So that polar group actually activates the surface of the silicon, and you get hydrosylation without light and without elevating the temperature. So this is pretty neat. You know, no one had seen that on our extended surfaces. So that curved surface makes the nanocrystals more reactive. So what we're really interested in is multiplex imaging. So that's one of the advantages of quantum dots over dyes, is you can put in quantum dots of different sizes that you can photoexcite at one wavelength and get different colors out. The other problem with silicon is because the indirect band gap, the line width for the emission is relatively broad compared to cadmium selenide. So it's a little difficult to do multiplex imaging just based on color. So what we use is the fluorescence lifetime of the silicon. So again, because of the indirect band gap of silicon, the fluorescence lifetimes are actually relatively long, 100 well, in the microsecond time range. And so this is quite different than like cadmium selenide nanocrystals with lifetimes of 50 nanoseconds, 10 nanoseconds, that sort of thing. And so what we can do is utilize that long lifetime, and what we utilize is the ability to do 2 photon excitation of the silicon quantum dots. So what we can do is take a high intensity laser, a pulse laser, and do 2 photon excitation. So instead of photoexciting at 400 nanometers, we photoexcite with 2 photons at 800 nanometers. And that actually works pretty well. So the 2 photon absorption cross sections for silicon nanocrystals are reasonably high, high enough anyway to use that to do imaging of the nanocrystals. So we've done some work in collaboration with Andy Dunn in biomedical engineering here at UT Austin, and they have a microscope where you can do 2 photon excitation of your dyes, and then you can do fluorescence lifetime gated imaging or time gated imaging. So we took cells and we fed them with two dyes of different colors, both which had relatively short lifetime, and then our silicon nanocrystals with long lifetime. And the color of one dye overlapped or was the same with the silicon nanocrystals. And so what you can do is we basically fed the cells with the 2 different dyes, and then these fluorescent silicon nanocrystals, and the cells just take up the nanocrystals. We didn't put any ligands of any kind on the nanocrystals. We just wanted to see where do the particles go in the cells. And so by doing this time-gated imaging, you can actually have the 2 dyes plus the silicon nanocrystals, and you can map the 3 different fluorophores pretty easily. So there actually aren't a lot of dyes or other kinds of nanocrystals with long lifetimes like this. So it's a fairly unique aspect of the silicon, and is pretty interesting. And so like Mike Saylor at UC San Diego has done some of this and kind of helped pioneer this in terms of the porous silicon particles that they would make. And I think it's a really powerful technique here. So I have a the student Ben Stacy, who joined the group a few years ago, and so he was putting a lot of different types of ligands onto the silicon nanocrystals, and that thermally promoted hydrosilation. Even though it works really well for these alkenes, you have to heat up to 180 C, 150 C, something like that. For a lot of ligands, that destroys the ligands depending on what the functional group is. So Ben found that really small nanocrystals, so about 2 nanometers, 3 nanometers in diameter, can actually be hydrosylated at room temperature. So this is pretty amazing. And this is without light, without UV activation, and without catalyst. Once you get above 4 nanometers in diameter, so the passivation no longer happens. So that high amount of surface curvature of the surface of the silicon really does make that surface much more reactive. You still have to let the particles sit there for like 12 hours, room temperature, so it's not ideal, but it is quite interesting that you can do hydrosilation at room temperature. These are some of the data. So if you try to passivate, about 5 nanometers in diameter is about the maximum size. Once you go above that, the passivation essentially stops. So what we found is that the alkenes at larger diameters will still bond to some extent, but at this sub-monolayer surface coverage, and so you can't redisperse the nanocrystals at that point. And so anyway, it's pretty interesting. We've been doing a lot of things where we want to do hydrosilation at room temperature, and one way that actually works pretty easily, so depending on your solvent system, is you can add AIBN, and this works pretty well. You get covalent silicon carbon linkage. So this is some additional work from Ben making gels of silicon nanocrystals. So we can passivate with a carboxylate group, and then we can disperse these in water and ethanol, and add nickel ions, and the nickel will cross-link the carboxylate groups, and you can make gels that way and things like that. So that's a bit about silicon. So now if we want nanocrystals that fluoresce further into the infrared, one obvious option is to go from silicon to germanium. So germanium we can make colloidally in a similar way to silicon, where we do growth in a solvent with metal seeds. So we can do tin-seeded growth of germanium nanowires, for example. And one reactant we use a lot is diphenylgermane. So diphenylgermane decomposes by phenyl redistribution. So these diphenylgermane groups in solution, I mean, you have to be at relatively high temperature. Usually we do this at 360 degrees C or higher. But the phenyl group, you don't actually have germanium carbon thermolysis. The 2 diphenylgermane groups come together in solution, and the phenyl groups hop. So they're kinetically labile. The phenyl groups hop from one germanium to the other. And so if you use diphenylgermane as a reactant, your highest yield you can get is 50%, or molar conversion is 50%, because you end up with tetraphenylgermane as a byproduct. So we've been able to kind of work around that to some extent by actually adding phenylsilane as a scavenger of those phenyl groups from the diphenylgermane. So I had a former student, Xiaotong Liu, who was trying to grow germanium nanowires using nickel seeds instead of gold. And what she found is the quality of the nanowires she was making was not particularly great. You can kind of see it in the SEM image in the blue here. What we had to do is add some phenylsilane that would actually take the phenyl groups from the germanium and speed up the decomposition kinetics for the for that phenylgermine, and that actually worked really well, and you can make really high quality nanowires. So you can play different games to use phenylgermine as a reactant for germanium, but at lower temperature and solution, when you don't have any seed particles and all that, it's really pretty tough to do much with that. So we use germanium diiodide quite a bit. Our first paper using germanium diiodide was back in 2005. It turns out in this reaction, we were adding troctylphosphine, which I'll come back to in a little bit. And troctylphosphine can be kind of important for some of these reactions. We didn't really know that back in 2005. We just wanted a high boiling solvent. But you can add bismuth, germanium diiodide. Here we're growing wires up at relatively high temperature, at like 350 C, and doing that in squalane, I think, at the time. So this germanium diiodide disproportionates, but what I'll talk about in a bit is that you can actually get reduction of the germanium to germanium 0 as well. So this is a TM image from a reaction a long time ago that one of my grad students, Do Chang Lee, had done. Do's a professor at KAIST now in Korea. But we were just kind of, he had done a lot of nanowire growth, and we were curious about germanium nanocrystals. And, you know, he showed, okay, you can make some germanium nanocrystals out of oleoamine. We were a little discouraged at the time because the particles didn't fluoresce or do anything particularly interesting, and it was difficult to control their size just by degrading germanium diiodide and oleoamine. But unlike silicon, you can actually make germanium nanocrystals fairly easily in a solvent by reciprocitation. The challenge is making them so you can control the size and get fluorescence out of them. That's the challenge. And so you can passivate, you know, germanium doing a hydrogenylation reaction with alkenes. You run into the same problems with silicon, that the alkene forms a irreversible germanium carbon bond, and that makes particle growth a challenge. So what we found is we can play games with mixtures of different kinds of ligands. So one of my former students, Jung Chul No, figured out that you can take germanium diiodide, you can do reactions in oleoamine, and you can add octadecene to these reactions, and you can get germanium carbon bonded with covalent bonded ligands in these reactions. And so what we do is we don't do a hot injection of the germanium. These are heat up reactions. So what you'll do is put the germanium diiodide into oleoamine with octadecene and heat that up. And what will happen is at relatively lower temperature, so something like 150 C, you'll see the germanium nanocrystals nucleate and start to grow in the oleoamine. And then as you're ramping the temperature up, you get hot enough where you get the hydrogenylation reaction to go, and the alkene will actually passivate the germanium particle. If you try to just throw germanium diiodide into this mixture at high temperature, a lot of times the alkene will just bond to the germanium and tie the germanium up, and you don't really get much. So these heat up reactions work pretty well, and you can make relatively monodispersed nanocrystals up to about 10 or 11 nanometers in diameter. And once you try to go above 11 nanometers in diameter, we just found you couldn't, okay, for whatever reason. I mean, it's just the combination of the kinetics and the bonding of the alkene, and we tried a bunch of different reaction conditions and doing hot injection and all of that sort of thing. Even hot injection in the oleoamine, you can form nanocrystals, but they only grow to a certain size, and then you add octadecene. So what we found is that we can use troctylphosphine to make significantly larger germanium. So if we do germanium nanocrystals with mixture, say, of oleoamine and troctylphosphine, if there's troctylphosphine in there, you end up making much, much larger germanium nanocrystals, these like giant, almost bulk kind of germanium particles. And the troctylphosphine is interesting because it doesn't seem to just speed up the reaction. The taupe seems to bind in complex with the germanium, actually slow down the nucleation event, but then once it happens at higher temperature, at say 180 or 200 degrees C, then you get this burst of growth and nucleation. And so what we found is we can control that by mixing in different amounts of oleoamine, troctylphosphine, and octadecene. So we can make nanocrystals over a wide range of sizes now of germanium, from 3 nanometers, maybe a little bit smaller than that, up to 18 or 20 nanometers in diameter. And so that's pretty neat. So we've got these nanocrystals. We can do small angle X-ray scattering on them. So these are dispersions, and you can do your Perot plots or however you want to do it. And the quality of the nanocrystals is quite good. And they're relatively well dispersed. You can see on H here at low Q, there's that kind of uptick in the scattering from the shape factor. So there's a bit of attraction and stickiness of the particles. So they're not perfect, but pretty good. And we've made some superlattices out of these and things like that. And so the cool thing about them is that they fluoresce. So this is under an IR camera, and it took us, we weren't really set up at UT for a while to do infrared photoluminescence. And so it took us a while to figure out, do these things fluoresce or not? And they do. And so we can make germanium nanocrystals that have size tunable fluorescence now, all the way sort of towards the band edge of germanium. So this is pretty exciting. We found that germanium nanocrystals, so far for us anyway, have been more difficult to make bright emitters. So all of the photoluminescence quantum yields of these materials I've shown here are less than about 0.1%. I mean, this is relative to dyes, and that's another thing. We're not set up to do absolute quantum yields. So that's, finding dyes that emit in the infrared, that's also part of a challenge with back out the quantum yield, but they're definitely not super bright. And so we're wrestling with that right now and trying to understand, is there something intrinsic to germanium that makes their fluorescence relatively weak compared to silicon, or are we just still not passivating the surface particularly well? And so germanium, the first transistors were made of germanium, and then people switched to silicon because of the surface oxide or lack of a stable oxide for germanium. So we're still wrestling with that, but we can make germanium nanocrystals fluoresce, size tunable, goes out in the near infrared. It's just still relatively weak. Okay, mercury telluride. So here are, to go even further into the infrared, mercury telluride is a pretty interesting material. It's a semi-metal, so it actually, as a bulk material, doesn't have a band gap. But when you make quantum dots, you can open up a gap, and you can tune essentially from no gap to pretty far in, not quite to the visible, but here it's shown down the bottom left in this plot is one micron wavelength, so pretty close to the visible. So these are a few nice review papers talking about mercury telluride and IR dots, in case you want to look those up. The synthesis of mercury telluride is pretty straightforward. So I'll talk a little bit about mixing in some different ligands. But you can just make nanocrystals with mercury chloride and oleoamine and do a hot injection with taupe telluride. Mercury telluride particles, you at least for us, we've found that we've got to grow at significantly lower temperatures compared to other nanocrystals. So maybe up as hot as 120 C, but these tend to be relatively low-ish temperature reactions. So just consider, I mean, once you understand that you have to use lower temperatures for the growth and that sort of thing, it's not too challenging to grow decent mercury telluride nanocrystals. So these are spherical nanocrystals and a bunch of size selective precipitations, and these particles were grown with mixtures of oleoamine and troctylphosphine oxide. And taupe also, but in using NMR, we can see that for sure the troctylphosphine oxide and oleoamine are both bound to the surface of the mercury telluride. So both those ligands are playing a role there. Again, we can do pretty decent small angle X-ray scattering measurements on dispersions of these. You see the that uptick in scattering intensity at low Q. So there's some attraction between particles, which ideally we don't really want, but we can still form superlattices even with that. And so, yeah, I guess I don't have a whole lot of X-ray scattering data in this talk, but this is some GSAX data of a superlattice of mercury telluride nanocrystals. So you can make superlattices. So what we're really interested in are their optical properties. So they behave as an ambipolar transistor. So at room temperature, you see both N and P type response. And then when you cool the particles down, you end up seeing N type response. And so that is electrons originating from tellurium vacancies. So sometimes we'll do these FET measurements on nanocrystals prepared with different ligands just to see, get a sense of how many vacancies are being created and things like that. So you can see that sort of thing from the FETs. The electron mobilities aren't particularly high, at least for the materials we make. I mean, you're talking like 0.1 centimeter squared per volt second, probably at room temperature. So you can make photodetectors out of these. The mercury telluride nanocrystals, at least spherical nanocrystals, most of them that we make just with oleoamine, if you drop them onto a device structure, there's really no photoconductive response. They're also very resistive and not particularly useful. But if you do an ethane dithiol exchange, for example, so kind of expose it to some ethane dithiol, and essentially you're stripping away some of the oleoamine, you can get some pretty decent detector response. So this is a layer of mercury telluride nanocrystals on an interdigitated array, kind of basically single element photodetector under 1 volt bias. And you can see that, so the black curve is under white light, red curve is under infrared light. So you see a couple things. When we do the infrared response, we're just blocking the white light, so it's a lower light intensity, so the response is lower. But you see a fast onset and a fast decrease. But under white light here, we see the slow response both on and off when you take the light source off. So depends on the sample. Some of the samples, we see that slow response in the infrared also, but it's more common to see the slow response with the higher light activation. So you can end up with higher energy photons, I think, driving some chemistry and surface chemistry and that sort of thing in these materials, which doesn't always happen with the infrared light. But that slow response is something that we try to get rid of and is related to the synthesis and the ligands and all of that. The interesting thing about the mercury telluride is that not all the nanocrystal quantum dots are photoconductive. And so that might sound like an obvious thing, but it turns out, at least from what we've found, is that the shape of these mercury telluride quantum dots is really important. So spherical mercury telluride quantum dots generally, if they do have a photo response, it's really weak. And in general, even with the ethane dithiol treatment is not particularly good. Whereas mercury telluride nanocrystals with anisotropic shapes, so tripods, so we call these tripods. So they're pretty interesting. So these are like branched nanocrystals of mercury telluride, and they seem to have a tripod structure. And so, you know, I'm familiar with tetrapods and octopods, but tripod, like a planar tripod, is kind of an interesting shape. But these mercury telluride nanocrystals, that's what they tend to form. So the branch structures are tripods. We can also play some games with the synthesis and make tetrahedra, and the spheres. They're all cubic in structure, and you can change the shape largely by mercury to tellurium ratio and some of the ligand chemistry. So you have the spherical mercury telluride nanocrystals. They tend to have poor photoresponse. The tetrahedral ones are a little bit better, so we can make those. But it's these tripods, these branched ones, that have really pretty good photoconductive response. And in the synthesis, we can change the arm width to some degree, but the arm length is a little bit easier for us to manipulate. So just turns out that way. We've been looking at what are the growth directions of those arms. So the arms can grow in the 1-1 direction quite a bit. Also the 1 or the 2-1-1 direction. Depends on the synthesis, the size of the wires. So a little bit larger arms tend to grow in the 2-1-1 direction. Thinner arms tend to grow in 1-1-1, and every so often we'll see an odd 1-1-0 growth. But usually it's 1-1-1 for very thin arms and 2-1-1 for a little thicker. And so we've thought a lot about what determines the shapes of these nanocrystals, and how do you manipulate that and do that with different kinds of ligands. And so we can actually grow some pretty thin arms on these tripods, even at room temperature. So that's something I think pretty interesting and unique about mercury telluride. You can actually make nanocrystals at room temperature. It takes maybe an hour for them to grow. So you know, maybe 3 hours, but it's not like 2 days or anything like that. And so these are some of the 1-1-1 arms. You can control the optical gap pretty easily in the shortwave infrared and the midwave infrared. Going the far infrared becomes a little more challenging, or at least to get decent photoconductivity response. So here in the bottom left, we have absorbance spectra, and in the middle is the photoconductivity response. And so even with nanocrystals with optical gap around 3.5 micron, 4 micron, you have a decent photo response. And so just getting into the far infrared is still what's a little bit challenging. But in the shortwave infrared, midwave infrared, with these like tripods, these anisotropic shapes, we can get some really good photo response, and also stable over time. So under certain conditions, we actually don't have to do the ligand exchange. And we've had devices that have been stable for months. You know, here we're looking at 6 months, but those devices now are over a year old. And so here what you see is mostly it's that slow response, that slow on response and off response. That's an issue, but they're very stable. And this was cooled. This was a camera that was cooled, but Jung Chul was pretty excited. He took his nanocrystals up to Chicago to this company, Sivananthan Laboratories, and work with a guy, Rich Pimpinella, and his team. and they put the quantum dots into a little camera structure, and Jung Chul was able to image a soldering iron and also his face. So still some work to do, but that was pretty exciting. So in the case of the mercury telluride, even though it's fairly straightforward to make colloidal nanocrystals of mercury telluride, and you can manipulate their shape a little bit and that sort of thing, the details of the ligands actually have a major impact on the performance of that material. So in the case of silicon, you take a situation where the ligands, it's really a challenge to just synthesize the materials, and the same is really probably true of germanium. But in all the cases, the ligands are having a dramatic impact on the optical properties of the materials. And in the case of silicon and germanium, for example, it's been more difficult to play games with inorganic shells. And so you're always relying on that organic capping ligand to the surface of the silicon and germanium to passivate the trap states and all of that. And so anyway, I'd be happy to answer any questions if anyone has any. Thanks.
Thank you, Brian. So that's quite an eye-opening presentation, seeing all these beautiful nanostructures. Are there any questions from the audience? Feel free to type in on the Q&A. So I actually have one question related to what you have been showing on the different shapes of this nanocrystals. That photo response, is that related to some inside the bulk, that band structure, or it's more like a surface, different geometry surface effect? Any comments on that?
Well, the photo response, the optical cutoff for like the wavelength, where when the wavelength is, or the energy is too low, the material doesn't absorb the light, like that's a shape, that's a size effect. Well, we think, so there's some things going on with like the actual absorption coefficient. So the rods, the materials with this anisotropic shape are much stronger light absorbers than the spheres at the same size. So there's something going on with the shape, changing some of the selection rules or something like that, oscillator strength, or and so the size is setting the optical gap, but the actual photo response and we tend to see some of these optical features will depend a bit on the shape also.
That's very interesting. Thank you, Brian. So
yeah,
thank you. There are no other questions from the Q&A session. So let's thank our plenary speaker, Brian, again. And a few quick final comments. So most of this APS rest of the workshops will take place starting Wednesday, but tomorrow there are 2 workshops. One is related to the data analysis on the X-ray spectrum, that's workshop 10. And the other is also a training related to vacuum that will take place tomorrow. And certainly tomorrow afternoon will be the APS symposium. So that will be given by the most of the talks from the experts within APS. I think so with that, I will just stop here. And thank you very much for all the speakers and also attendees for today's section, and hoping to see each other again for the next few sections and workshops. Thank you, and have a good rest of the day.
Thank you.